Somewhere beneath modern cities, beneath deserts, forests and oceans, the ancient world is still there. Not as legends, but as real places waiting in darkness. Collapsed temples no one remembers building, hidden chambers sealed for thousands of years, and entire cities erased so completely that history nearly forgot they existed. Every time archaeologists uncover one of these sites, the same feeling returns. The past is far less understood than we want to believe. Because ancient mysteries are not just about lost civilizations, they're about missing knowledge, techniques that vanished, stories that were never written down, and evidence that survived longer than the explanations behind it. The deeper humanity searches into its past, the more the ancient world begins to resemble a puzzle that was never fully preserved. Above the Al-Halaa, Azani Valley in eastern Georgia, the ruins of Nekresi Monastery have survived earthquakes, freezing winters, and nearly 1,500 years of erosion. But the real mystery is not why the monastery still stands. It is how its builders possessed engineering techniques that, in some cases, resemble technologies rediscovered only in the modern era. Although the monastery was known locally for centuries, major archaeological investigations began during the 20th century when Soviet-era researchers uncovered older structures buried beneath the Christian complex. Excavations revealed traces of pre-Christian temples, advanced drainage systems, unusual mortar compounds, and hidden architectural layers dating as far back as late antiquity. What initially appeared to be a simple medieval monastery slowly became one of the most technically puzzling ancient sites in the Caucasus region. One of the first mysteries surrounding Nekresi involves its survival against seismic activity. The monastery sits near tectonically active zones connected to the Greater Caucasus Mountains, where earthquakes have repeatedly damaged settlements throughout history. Yet large portions of Nekresi remain standing while many nearby structures collapsed over the centuries. Modern geological surveys discovered that the builders did not use a simple stone foundation. Instead, they created layered substructures composed of crushed rock, compacted soil, lime mortar, and porous filler materials capable of dispersing seismic vibration. Engineers comparing the structure to Roman anti-seismic construction methods found striking similarities to techniques used in parts of ancient Italy, nearly 1,000 kilometers away. What makes this more mysterious is the presence of volcanic ash compounds inside some mortar samples. Pozzolanic materials are famous for strengthening Roman concrete because they chemically react with lime and water to form durable crystalline bonds. The problem is that eastern Georgia has no major nearby volcanic ash source capable of easily supplying such material during late antiquity. Researchers still debate whether these compounds were imported through ancient Persian trade routes or produced using a lost regional formula. Either explanation raises difficult questions. Transporting large quantities of specialized material into mountainous terrain during the 4th or 5th century would have required a surprisingly organized logistical system. Another unexplained feature involves temperature regulation. Summers in Cahuachi can exceed 35 degrees Celsius, while winters regularly fall below freezing. Despite this, several chambers within the monastery maintain unusually stable internal temperatures throughout the year. Thermal imaging studies revealed hollow air channels concealed inside thick stone walls. These cavities appear to create natural airflow circulation, similar to modern passive ventilation systems. Warm air rises through narrow vertical shafts, while cooler air is pulled through lower openings, stabilizing temperatures without mechanical assistance. This principle resembles the Badgir wind catchers of ancient Persia and the cooling systems used in desert yakhchals. However, Nekresi exists in a completely different environmental setting. The Caucasus climate is colder and wetter than the Iranian plateau. making the adaptation of such techniques highly unusual. Some architectural historians believe the builders may have inherited engineering knowledge through contact with Persian craftsmen during periods of Sasanian influence. Others argue the system evolved independently. Either way, the sophistication of the airflow design exceeds what historians once assumed about early medieval Caucasian architecture. The greatest technological mystery at Nekresi may be its mortar. For decades, scientists studying the monastery noticed that certain sections of masonry showed extraordinary resistance to moisture and cracking. While ordinary medieval mortar often weakens after centuries of freeze-thaw cycles, parts of Nekresi's original binding material remain remarkably stable even after roughly 1,500 years of exposure. Microscopic analysis revealed dense crystalline structures forming inside the mortar over time. Instead of simply decaying, the material appears to continue chemically evolving centuries after its original creation. This phenomenon has drawn comparisons to Roman pozzolanic concrete, used in harbours such as Caesarea and Portus, where ancient marine structures sometimes outperform modern cement in saltwater conditions. Researchers discovered traces of lime, volcanic minerals, finely crushed ceramics, and possibly organic additives mixed into the Nekresi mortar. Some samples also contain microscopic reactions suggesting self-healing behaviour. When small fractures form, dissolved minerals slowly recrystallize inside the cracks, partially sealing the damage naturally. Modern engineers have attempted to reproduce similar compounds in laboratory conditions, yet no recreation has perfectly matched the durability of the original material. Even slight changes in mineral ratios dramatically alter the mortar's strength and moisture resistance. What makes this especially mysterious is the level of practical chemistry required. Producing stable lime mortar alone already demands precise temperature control during limestone burning. Adding volcanic compounds or ceramic particles in exact ratios implies generations of accumulated experimentation. Yet almost no written records survive explaining how Caucasian builders developed or transmitted this knowledge. The mystery becomes even deeper when compared with modern Portland cement. Although modern concrete can achieve enormous compressive strength, it often deteriorates within 50 to 100 years under severe environmental stress. Some sections of Nekresi's mortar have already survived more than 15 centuries. To some material scientists, the monastery represents evidence that ancient builders may have mastered long-term durability better than many industrial systems today. The monastery's main chapel also displays strange acoustic behavior. Researchers conducting low-frequency sound tests discovered that the curved stone vault amplifies chanting far more efficiently than expected for a relatively small chamber. Specific frequencies resonate through the structure with unusual clarity, creating the illusion of a much larger interior space. Acoustic engineers found that the geometry of the walls reduces echo distortion while enhancing vocal depth. Similar effects are famous in Byzantine cathedrals such as Hagia Sophia, yet Nekresi achieved related acoustic complexity on a much smaller scale. Some historians believe the effect was accidental. Others argue it was intentionally engineered for religious ceremonies. If deliberate, the builders possessed a surprisingly advanced empirical understanding of sound wave behavior centuries before formal acoustic science existed. Perhaps the most controversial discovery at Nekresi lies beneath the Christian complex itself. Excavations uncovered evidence of an earlier fire temple possibly linked to Zoroastrian practices during periods of Persian control over eastern Georgia. Archaeologists identified ritual fire platforms and carefully designed smoke ventilation systems capable of maintaining combustion in enclosed spaces. The ventilation channels are unusually efficient for such an ancient structure. Oxygen flow appears to have been carefully regulated to sustain ritual flames continuously without filling the chambers with smoke. Similar engineering principles can be observed in sophisticated Persian fire temples much further south. This discovery transformed Nekresi from a purely Christian monument into evidence of overlapping civilizations, religions, and technological traditions. The monastery may represent a rare architectural bridge between Persian engineering and early Christian Caucasian construction. Geophysical surveys have detected underground anomalies beneath Nekresi Monastery, leading researchers to suspect the existence of buried tunnels, storage chambers, or ancient ritual passages. Even more mysterious, some of these structures appear aligned with the position of the sun during equinoxes and solstices, similar to ceremonial sites found across Eurasia. Because the hillside remains structurally fragile, full excavation has never been completed, leaving the underground secrets of Nekresi unsolved to this day. Do you think the builders of Nekresi Monastery truly possessed engineering knowledge far ahead of their time, or are these mysteries still hiding a deeper explanation? Share your thoughts in the comments below. On the western coast of Anatolia, the forgotten Ionian city of Klazomenai may contain evidence of something history was never supposed to see: an industrial-scale production system operating nearly 2,600 years ago. Long before Rome reached its peak, and centuries before most Greek cities mechanized labor, Klazomenai appears to have mastered large-scale engineering, seismic-resistant foundations, precision ceramics, and hydraulic harbor control with a level of sophistication that still unsettles archaeologists today. The ruins of Klazomenai were gradually identified through excavations beginning in the 1920s, but the city shocked researchers in the late 20th century when archaeologists uncovered what is now considered one of the oldest known olive oil workshops ever discovered. Further excavations revealed advanced harbour structures, engineered foundations, and highly sophisticated painted sarcophagi that survived more than 2,500 years almost intact. The single most controversial discovery at Klazomenai was its olive oil production complex, dated to around the late 7th and early 6th century BCE. At first glance, it seemed like a standard Greek workshop. But once researchers reconstructed the system, the site began to look less like a primitive press and more like an organized industrial facility. The workshop contained rotary crushing stones, pressing platforms, fluid separation channels, and carefully angled collection basins designed to separate oil from water using gravity. The engineering precision immediately stood out. The channels were cut with consistent slopes, allowing liquid to move efficiently without stagnation. Some sections appear mathematically optimized to minimize waste. What shocked archaeologists most was scale. Most Greek olive oil production during this period was small and household-based, yet Klazomenai's facility appears designed for continuous, high-volume output. Experimental archaeology conducted by researchers in Turkey suggested the installation could process quantities far beyond typical family consumption, implying organized export production centuries before historians believed such economic systems existed in the Greek world. Comparisons with later Roman olive oil factories reveal disturbing similarities. Roman industrial presses from the 1st century CE used many of the same hydraulic principles seen at Klazomenai, but those Roman systems appeared nearly 600 years later. This raises an uncomfortable possibility. Either Ionian engineers developed industrial production techniques far earlier than previously believed, or technological knowledge from cities like Klazomenai was later absorbed into Roman engineering traditions and largely forgotten in the historical record. The mechanics themselves remain partially unexplained. Researchers still debate how workers synchronized crushing, pressing, and fluid separation so efficiently without advanced gearing systems. Some scholars suggest the workshop represents an evolutionary stage of mechanical engineering that disappeared after the Persian invasions destabilized the Ionian coast. Even more mysterious is the city's apparent understanding of material durability. The pressing floors were built using stone compositions resistant to oil corrosion and long-term mechanical stress. Some surfaces show surprisingly low wear despite what may have been decades of heavy production. Modern analyses found evidence of intentional aggregate selection in the flooring mixture, suggesting the builders understood which minerals resisted chemical degradation best. For many historians, Klazomenai forces a deeply uncomfortable question. How could a city from the archaic Greek period operate something resembling a semi-industrial production line centuries before the Industrial Revolution was even imaginable? Klazomenai sat in one of the most earthquake-prone regions of the eastern Aegean. Modern Western Turkey remains highly active tectonically today. Yet excavations show that many structures in the city survived repeated seismic activity for centuries. Beneath several buildings, archaeologists discovered layered foundation systems combining compacted soil, rubble, clay, and flexible stone packing. Rather than constructing rigid foundations, the builders appear to have intentionally created semi-flexible bases capable of dispersing seismic energy. This resembles principles used in modern earthquake engineering. Some walls also contain tiny expansion gaps that may have reduced structural cracking during tremors. In certain areas, different foundation styles were used only meters apart depending on soil composition, implying the builders understood that various ground conditions required different stabilization methods. That level of geotechnical adaptation is astonishing for the 6th century BCE. Comparisons are often made with later Roman seismic techniques used in Pompeii after earthquakes in the 1st century CE. Yet Klazomenai predates those adaptations by hundreds of years. Some engineers believe the Ionian Greeks may have developed empirical earthquake-resistant architecture through generations of observing tectonic behavior along the Anatolian coast. Klazomenai was not simply a coastal settlement, it was a maritime trading hub deeply connected to Lydia, Phoenicia, Egypt, and the Black Sea. But what makes the harbour mysterious is the apparent sophistication of its hydraulic planning. Submerged stone structures near the ancient coastline were positioned at angles that reduced wave force while stabilising docking zones. Modern hydrodynamic simulations conducted on similar ancient harbours show that even small angular changes dramatically affect current flow and sediment accumulation. Some sections of the harbour seem specifically designed to reduce silting, one of the greatest problems for ancient ports. The question is how Ionian engineers calculated these effects without modern fluid dynamics, surveying lasers, or mathematical modelling software. Researchers suspect centuries of practical maritime observation may have produced an advanced body of empirical engineering knowledge now almost entirely lost. Ancient sailors from the Aegean likely understood wave behaviour with far greater precision than surviving written texts suggest. Klazomenai also produced some of the finest painted terracotta sarcophagi in the Greek world. Many still retain black, red, and cream pigments after more than 2,500 years. That durability is highly unusual. Laboratory analysis indicates the pigments were fired under carefully controlled oxygen conditions. Even minor fluctuations inside the kiln could have ruined the coloration entirely. Maintaining such consistency required extraordinary temperature regulation. Some ceramics may have exceeded firing temperatures of 900 to 1,000 degrees Celsius. Achieving this in ancient kilns required airflow controls sophisticated enough to rival techniques later perfected in classical Athens. The paint adhesion is another mystery. Certain pigment layers chemically bonded to ceramic surfaces so effectively that they resisted salt air, humidity, and biological erosion for millennia. In coastal conditions, most painted surfaces degrade rapidly. Yet some Klazomenai sarcophagi preserved line detail with astonishing clarity. This has led some researchers to speculate that Ionian ceramic workshops possessed proprietary firing techniques or mineral recipes that vanished after regional political collapse. During the 5th century BCE, much of Klazomenai relocated from the mainland to a nearby island for defensive reasons. To connect the island with the coast, the inhabitants constructed a massive causeway across shallow marine terrain. Building stable infrastructure over coastal sediment is extremely difficult even with modern engineering. Saltwater erosion, shifting seabeds, and wave pressure constantly destabilize foundations. Yet geological studies suggest the ancient causeway survived for generations. Its builders appear to have layered stone fill according to weight distribution principles that minimized collapse. Some sections used larger outer stones with compacted smaller fill toward the interior, a method still recognizable in modern marine embankment engineering. Again, the same question emerges. How did these people understand structural load behavior so well without formal engineering science? Klazomenai existed during the intellectual explosion of the Ionian world, a time when ancient philosophers, astronomers, and engineers began explaining nature through observation instead of mythology. Many historians believe Klazomenai was part of a technological exchange network stretching from Anatolia to Egypt and Mesopotamia. If true, many ancient Greek technologies may actually have been the result of centuries of shared knowledge between multiple civilizations. But wars, earthquakes, and the collapse of Ionia caused much of this knowledge to disappear. Unlike Rome, which left behind vast technical records, Ionian knowledge appears to have been passed down mainly through oral tradition, and vanished along with the cities themselves. Do you think cities like Klazomenai were far more technologically advanced than mainstream history admits? Or are we simply underestimating the engineering abilities of the ancient world? Let us know your thoughts in the comments below. In Pakistan's Swat Valley, Butkara stupa survived earthquakes, invasions, and 2,000 years of erosion. Yet some archaeologists believe its most advanced technology is still unexplained. The site was first systematically excavated in the 1950s by the Italian Archaeological mission led by Domenico Faccenna. Beneath layers of collapsed stone, archaeologists discovered something unexpected. The stupa had not been built once. It had been enlarged repeatedly for centuries, each new structure wrapped precisely around the older core without destroying it. That discovery transformed Butkara from a forgotten Buddhist ruin into one of the strangest engineering puzzles in ancient Gandhara. Most ancient monuments were rebuilt by demolishing earlier structures. But Butkara followed a completely different principle. Archaeologists identified multiple construction phases dating from roughly the 3rd century BCE to the 10th century CE. Instead of replacing the original Ashokan stupa, builders continuously encased it inside newer stone shells. This sounds simple until the engineering implications are understood. Every expansion changed the weight distribution of the monument. A slight asymmetry could have shifted the center of gravity, creating stress fractures that would eventually collapse the structure. Yet the stupa remained remarkably stable for over 2,000 years in one of the most seismically active regions of Asia. Modern engineers use layered shell construction and stress calculations through computer modeling. The builders of Butkara had none of those tools. Still, the monument maintained structural balance through repeated enlargements across centuries. Similar layered expansion can be seen at sites like Borobudur or some Mesoamerican pyramids, but Butkara's precision is unusual because the entire structure relied heavily on brittle schist stone rather than massive limestone blocks. One of the greatest puzzles at Butkara is the material itself. The monument was built largely from grey schist, a metamorphic rock notorious for splitting along natural layers. Unlike granite, schist is extremely difficult to shape into uniform architectural blocks because it fractures unpredictably under pressure. Yet at Butkara, many joints fit with astonishing precision. Some gaps between stones are only a few millimeters wide. Archaeologists found evidence that the builders cut the blocks with highly controlled angles, despite using what should have been relatively primitive Iron Age tools. This raises a major question. How did ancient Gandharan craftsmen achieve such consistency with a material considered unstable, even by modern stoneworkers? Comparisons are often made with Inca polygonal masonry in Peru, or the granite cutting techniques at Great Pyramid of Giza. However, those civilizations worked with far more predictable stone types. Schist behaves differently. Even today, quarry workers avoid using it for high-load precision structures because thermal expansion and moisture penetration can accelerate cracking. But Butkara somehow overcame those limitations. The Swat Valley lies near the collision zone between the Indian and Eurasian tectonic plates. This region has experienced destructive earthquakes for thousands of years. Heavy stone stupas should not survive long in such conditions. Yet parts of Butkara remained standing after centuries of seismic activity. Excavation reports revealed something unusual beneath the structure. Certain foundation layers appear intentionally arranged to distribute stress outward, rather than concentrate it vertically. Some researchers compare this to primitive seismic buffering systems. Modern earthquake engineering uses flexible foundations and force dispersal geometry. But Butkara obviously lacked steel reinforcements or rubber dampers, yet the builders may have discovered similar principles through empirical observation. The layered stone arrangement possibly reduced resonance vibrations during tremors. What makes this even stranger is timing. Sophisticated anti-seismic architecture is usually associated with Roman engineering or much later Japanese wooden construction. But Butkara may preserve evidence that ancient Gandharan builders understood practical earthquake mitigation more than a millennium earlier. The sculptures around Butkara stupa reveal another mystery. Many statues display distinctly Hellenistic proportions. Realistic drapery folds, symmetrical facial geometry, and anatomical detailing rarely seen in early South Asian art. Historians usually attribute this to the aftermath of Alexander the Great's campaigns in Central Asia around 327 BCE. Greek influence entered Gandhara through Indo-Greek kingdoms and later Kushan patronage. But the precision of the artistic transfer is extraordinary. Some Buddha statues from Gandhara resemble Mediterranean marble sculpture more closely than traditional Indian religious art. The carving techniques used on schist achieve deep shadow effects and layered clothing textures comparable to Hellenistic workshops thousands of kilometers away. Without printing, global trade networks, or modern communication, how did such specialized artistic mathematics spread so accurately across Eurasia? Even more mysterious is the possibility that Gandharan sculptors were using proportional systems similar to classical Greek geometry. Several statues show recurring ratios in facial spacing and body dimensions, remarkably close to idealized Hellenistic canon measurements. Surrounding the main monument are more than 200 subsidiary stupas and shrines. At first glance, they seem randomly distributed, but aerial surveys revealed repeating spatial patterns around the central core. Many structures maintain surprisingly consistent distances despite being built across different centuries. This suggests long-term planning rather than chaotic religious expansion. Some archaeologists believe the layout may have reflected ritual movement paths or symbolic cosmology. Others suspect astronomical alignment played a role, though evidence remains inconclusive. The statistical consistency itself is difficult to explain. Ancient builders without aerial perspectives somehow preserved large-scale spatial coherence across generations. Similar mysteries exist at Teotihuacan and Angkor Wat, where citywide geometry appears too organized for purely organic development. Butkara may represent a smaller yet equally sophisticated example of ancient spatial engineering. Today, Butkara appears grey and weathered, but chemical analysis of surviving fragments suggests the complex was once vividly painted. Microscopic traces of red ochre, azurite blue, and mineral-based pigments were found on several sculptures. The problem is survival. The Swat Valley experiences intense seasonal rain, strong UV exposure, and major temperature fluctuations. Organic paint should have disappeared centuries ago. Yet pigment residues endured. Researchers suspect ancient artisans mixed mineral powders with organic binding agents that created unusually durable coatings. Similar mysteries exist with Maya blue in Mesoamerica, a pigment capable of surviving tropical climates for over 1,000 years. At Butkara, the exact composition remains uncertain. If reconstructed, it could reveal sophisticated chemical knowledge hidden inside what is usually described as purely religious art. The greatest mystery at Butkara may be invisible. Deep inside the stupa, archaeologists discovered relic chambers positioned extraordinarily close to the geometric center of successive construction phases. This is astonishing because the monument was enlarged repeatedly over centuries. Maintaining central alignment during a single construction project is difficult enough. Preserving it across generations without modern surveying equipment borders on impossible. Even a small angular deviation during one expansion phase would shift the central axis dramatically over time. Yet measurements show remarkable continuity between multiple layers of the monument. This suggests the builders used a standardized system of geometry and reference points, far more advanced than previously assumed for ancient Gandhara. Some researchers speculate they employed plumb-line triangulation, calibrated measuring rods, or astronomical orientation methods. Others believe master builders passed down exact proportional formulas through guild traditions over centuries. The mathematical challenge becomes clearer when compared with medieval European cathedrals. Many Gothic builders struggled to maintain axial symmetry, even with written plans and metal tools. Butkara achieved astonishing consistency in a far earlier era, using fragile materials and likely oral engineering traditions. The deeper archaeologists study the monument, the less accidental its geometry appears. Do you think the builders of Butkara Stupa possessed engineering knowledge far ahead of their time? Or are we still missing a huge piece of ancient history? Let us know your theory in the comments below. Buried for over 1,300 years within the collapsed mud brick ruins of modern-day Tajikistan, the ancient city of ancient Penjikent preserved some of the most mysterious wall paintings ever discovered along the Silk Road. Inside its abandoned homes and temples, archaeologists uncovered murals whose colors, chemistry, and artistic precision still challenge modern science. The site was first discovered in 1946 by Soviet archaeologist Alexander Belenitsky, after locals reported strange ruins emerging from the desert terrain around Penjikent. Excavations soon revealed an entire Sogdian city, frozen beneath collapsed architecture, including palaces, temples, workshops, and hundreds of painted walls preserved under layers of clay and dust. The greatest mystery surrounding the Penjikent murals is not the imagery itself, but the survival of the paint. Scientific studies revealed that the artists used highly complex mineral pigments, including lapis lazuli blue, cinnabar red, malachite green, gypsum white, and carbon black. Some of these materials traveled enormous distances through Silk Road trade routes. Lapis lazuli likely came from Afghanistan's Badakhshan mines over 500 kilometers away, while cinnabar sources may have originated from Central Asian mercury deposits. Yet the real puzzle is how these pigments remained visible after more than 13 centuries inside unstable mud brick buildings, exposed to earthquakes, heat, moisture, and total structural collapse. Modern conservation teams discovered that many murals were not painted using true wet fresco methods like those seen in Roman villas or Renaissance Italy. Instead, Penjikent artists mainly painted onto dry plaster surfaces. Under normal conditions, drywall pigments deteriorate far faster because the paint does not chemically bond with wet lime plaster. Roman frescoes at Pompeii survived largely because volcanic ash sealed the walls quickly. Penjikent had no such protection. The city experienced seismic activity, seasonal humidity fluctuations, salt crystallization, and roof collapses. By all known conservation models, most of the paintings should have disappeared centuries ago. Microscopic analysis revealed another anomaly. The murals contain multiple ultra-thin paint layers separated by specially prepared clay coatings, sometimes thinner than a human fingernail. Researchers also found traces of unusual organic binders mixed into the pigments, but most compounds degraded beyond identification. Some specialists suspect plant gums, egg-based mixtures, or animal-derived proteins were used in combinations still not fully understood today. Even more mysterious, certain pigments penetrated deep into plaster pores in ways resembling partial chemical fusion, rather than simple surface painting. Comparisons with other ancient mural traditions make the mystery even stranger. Egyptian tomb paintings preserved their colour partly because of extremely dry, sealed environments. Roman frescoes relied on wet lime carbonation. Chinese Dunhuang cave murals survived through cave isolation and mineral stability. But Penjikent combined unstable mud brick structures, open urban architecture, and dry wall techniques, conditions considered among the worst possible for long-term mural survival. Yet some sections still retained strong reds and blues visible after over 1,300 years. Modern laboratories have attempted to recreate the Penjikent preservation process using similar mineral pigments and clay compositions, but results remain inconsistent. Many replicas begin flaking within decades. The original murals survived more than a millennium underground. That gap remains largely unexplained. Another technological mystery lies in the construction of the walls themselves. Detailed scans show the Sogdian artists used carefully engineered plaster systems involving multiple clay and gypsum layers designed to regulate moisture absorption. In several rooms, researchers found that the wall surfaces had been deliberately roughened before painting to increase pigment adhesion. Some plaster layers were compressed with remarkable uniformity despite the absence of advanced tools. What shocks archaeologists is the level of precision achieved in the 7th and 8th centuries. Certain sections reveal pigment layering only fractions of a millimetre thick. The artists clearly understood how mineral particles reacted differently to porous and non-porous surfaces. Similar controlled layering techniques would not become common across parts of Central Asia until centuries later. The engineering resembles knowledge seen in later Persian and Byzantine wall preparation systems, yet Penjikent predates many of those examples. Some experts believe the Sogdians developed an independent technical tradition now mostly lost to history after the Islamic conquests of Central Asia. The murals themselves appear almost surreal. Unlike neighbouring Buddhist cave art or formal Persian court imagery, Penjikent scenes are chaotic, violent, and filled with hybrid creatures, demons, feasts, celestial symbols, funerary rituals, and massive battle scenes. Entire walls function like visual storyboards, with sequential scenes unfolding across rooms almost like ancient cinema. One mural depicts armoured warriors battling giant monsters beneath floating circular symbols that resemble astronomical diagrams. Another shows masked figures carrying bodies through ritual ceremonies, while musicians and animals surround them. Historians believe many scenes relate to lost forms of Zoroastrian mythology, but no surviving written explanations exist. This creates one of the greatest intellectual mysteries of the Silk Road. The Sogdians were among the most important traders in Eurasia, connecting China, Persia, India, and Byzantium. Yet most of their literature vanished after the Arab conquests of the 8th century. Penjikent may preserve fragments of stories, religious systems, and cosmological beliefs that no longer exist anywhere else on Earth. Some murals even contain visual themes later associated with the Persian epic Shahnameh, particularly stories connected to the hero Rustam. The problem is chronological. Many Penjikent paintings predate the final compilation of the Shahnameh by centuries. This suggests the Sogdians may have preserved much older Iranian oral traditions now completely lost. Penjikent stood in a seismically dangerous region near mountain fault systems. Earthquakes repeatedly struck the Zarafshan Valley throughout history. Yet many mural chambers remained sufficiently intact to preserve delicate wall paintings beneath collapsed debris. Excavations revealed that Sogdian builders used timber reinforcement frameworks inside mud brick walls. Wooden beams were embedded horizontally throughout structures, allowing buildings to flex during tremors rather than shatter instantly. Similar anti-seismic principles appear later in Persian and Himalayan and mountain architecture. Ironically, the collapse itself may have protected the murals. In many structures, roofs fell inward in layered sections, creating sealed chambers that shielded paintings from wind and sunlight. Some archaeologists compare the process to a controlled burial system accidentally created by architectural design. The preservation effect resembles Pompeii in certain ways, but with one critical difference. Pompeii was sealed by volcanic ash in hours. Penjikent was gradually buried beneath collapsing earthen architecture over decades or centuries. This slower burial should have exposed murals to far greater environmental damage. Yet many survived anyway. Perhaps the strangest question is why the murals remained stable underground for so long. Normally, buried wall paintings suffer catastrophic destruction from moisture migration and salt crystallization. As groundwater evaporates, salt crystals expand inside plasterpores and break the paint apart. This process destroys countless ancient murals worldwide. But Penjikent existed in an unusual environmental balance. Scientists believe the mineral-rich clay, low oxygen conditions, dry desert atmosphere, and rapid debris accumulation created a rare preservation chamber. Dust layers may have acted like insulating blankets that stabilized humidity fluctuations for centuries. Even modern conservators struggle to preserve the murals after excavation. Some fragments began deteriorating almost immediately upon exposure to open air. Museums controlling the surviving paintings now use specialized humidity regulation systems because the ancient pigments remain extremely sensitive to environmental change. This creates a disturbing possibility. The murals may have survived underground more effectively than they can survive inside modern museums. Do you think the Sogdians discovered artistic and chemical techniques far ahead of their time? Or are we still missing a huge chapter of ancient human history? Share your thoughts in the comments below. Harireh ancient city rises from the coral surface of Kish Island in southern Iran, surrounded by salt air, extreme heat, and almost no permanent fresh water. Yet nearly 1,000 years ago, a thriving city stood here for centuries. What archaeologists discovered beneath its ruins suggests Harireh may have possessed environmental engineering technology, far more advanced than historians once believed. The ruins of Harireh were formally identified during archaeological surveys on Kish Island in the 20th century, with major excavations intensifying in the 1970s and 1980s. Researchers uncovered residential districts, underground water systems, workshops, ports, and massive coral stone structures spread across nearly 120 hectares. The deeper archaeologists dug, the stranger the city became. Harireh should never have survived as a major urban centre. Kish Island receives extremely low annual rainfall, often less than 150 millimeters per year. Summer temperatures regularly exceed 40 degrees Celsius. while humidity from the Persian Gulf accelerates salt corrosion on stone and metal. Even modern infrastructure struggles in such conditions. Yet between the 8th and 14th centuries, Harireh became an important trade hub connecting Persia, India, East Africa, and the Arabian Peninsula. Historical records describe flourishing markets, wealthy merchants, and advanced craftsmanship. The question is simple. How did a medieval city sustain thousands of people on an island with almost no natural freshwater? The answer may lie underground. Archaeologists discovered carved channels, underground reservoirs, and complex drainage systems cut directly into fossilized coral bedrock. Some sections appear designed not only to transport water, but also to cool it before distribution. Researchers compared parts of the network to the Persian Qanat systems used on the mainland, yet Harireh's version appears adapted specifically for humid island conditions. Several engineers studying the ruins proposed a controversial possibility. Harireh's inhabitants may have partially relied on atmospheric moisture collection. The Persian Gulf maintains high humidity levels year-round, often above 60 to 70% at night. If cool underground chambers forced condensation from humid air, the city may have produced fresh water through passive climate engineering centuries before modern atmospheric water generators. No surviving written record fully explains the system. Much of the underground structure remains buried. One of the most shocking aspects of Harireh is not what collapsed, but what did not. The city's walls were constructed largely from coral stone and lime-based mortar, materials normally vulnerable to salt crystallization. In coastal environments, salt enters porous stone, expands during evaporation, and slowly destroys structures from within. Across the Persian Gulf, many later coastal buildings deteriorated within a few centuries because of this process. Yet sections of Harireh survived nearly 1,000 years under constant exposure to salty air and sandstorms. Material analysis revealed unusual mineral compositions inside the mortar. Researchers found mixtures of lime, ash, crushed shell material, and marine minerals that appear capable of reducing internal salt expansion. Some samples even displayed partial self-sealing behavior when exposed to moisture. This has led to comparisons with Roman marine concrete, which famously becomes stronger through long-term contact with seawater due to rare mineral reactions involving volcanic ash. But Harireh existed far from the Mediterranean world. If the builders independently developed similar anti-corrosion chemistry, it suggests ancient engineers across different civilizations may have discovered advanced material science through trial and observation long before modern chemistry existed. The precision is especially surprising considering the environment. Kish Island experiences extreme thermal expansion between day and night temperatures. Any construction error would gradually fracture walls over decades. Yet many Harireh foundations remained structurally stable for centuries. Inside several major structures, archaeologists identified narrow corridors, ventilation shafts, elevated openings, and hollow subfloor chambers. At first, these seemed like ordinary architectural features. Later airflow simulations changed that assumption completely. Modern computational models showed the buildings could generate passive convection currents. Hot air naturally rose through upper vents, while cooler air circulated through shaded lower chambers. Some reconstructed thermal models suggest interior temperatures may have remained 8 to 12 degrees Celsius, cooler than outside conditions. That difference is enormous in Gulf climates. What makes the system remarkable is its efficiency without mechanical energy. The principles resemble modern passive cooling architecture now promoted in sustainable engineering projects across the Middle East. Similar concepts exist in Persian wind catchers called badgears, but Harireh's implementation appears unusually integrated into entire building complexes rather than isolated towers. Some archaeologists believe the city's architects possessed a highly refined understanding of airflow, pressure differentials, humidity control, and thermal mass. They may not have known the physics mathematically, but centuries of experimentation could have produced engineering knowledge almost impossible to detect from historical texts alone. The result was essentially a natural air conditioning system operating nearly 1,000 years before electricity. The most controversial discoveries at Harireh came from its industrial workshops. Excavations uncovered evidence of glass production, ceramic processing, and high-temperature furnaces capable of extremely stable heating conditions. Fragments of finished glassware found at the site display exceptional transparency and colour consistency despite centuries buried in salty soil. Producing such glass was extraordinarily difficult in the medieval world. Even tiny fluctuations in furnace temperature can introduce bubbles, cloudiness, fractures, or colour distortion. To manufacture high-quality transparent glass, temperatures often must remain between roughly 1,100 and 1,300 degrees Celsius for extended periods with controlled oxygen flow. Achieving that consistency without modern thermometers or industrial fuel systems should have been incredibly challenging. Yet some Harireh glass samples rival luxury Islamic glassware produced in major centres like Cairo or Damascus. Researchers studying furnace remains discovered sophisticated airflow channels built beneath firing chambers. These may have allowed craftsmen to regulate combustion intensity with surprising precision. Certain kiln layouts also appear designed to recycle heat internally, improving fuel efficiency while stabilizing temperatures. This is where the mystery deepens. Kish Island possessed limited natural fuel resources. Large-scale glass production requires enormous energy consumption. Historians still debate how Harireh maintained industrial furnaces at such temperatures on a relatively resource-poor island. Some theories suggest imported charcoal networks from mainland Persia. Others argue the workshops operated using highly optimized furnace engineering far beyond what historians previously attributed to the region. Chemical analysis of several glass fragments revealed unusually low impurity levels, suggesting extremely refined raw material preparation. Some pieces also contained mineral additives likely used to stabilize color during heating. To modern materials scientists, the workshops imply a forgotten level of industrial specialization. Harireh may not simply have been a trading city, it may have been a technological manufacturing center, operating at a level historians underestimated for centuries. Several structural axes inside Harireh align closely with solar positions during seasonal transitions. While this could be coincidence, maritime historians believe the orientation may have served practical purposes tied to navigation and seasonal trade winds. The Persian Gulf was one of the ancient world's busiest maritime corridors. Merchants sailing between Persia, India, and East Africa depended heavily on monsoon cycles, celestial navigation, and predictable currents. Even small miscalculations could strand ships in dangerous waters for months. Some scholars propose Harireh functioned partly as a navigational coordination center. Elevated observation points near the coast may have allowed tracking of stars, sunrise positions, and seasonal atmospheric patterns. Similar astronomical maritime relationships existed in places like ancient Oman, Indian Ocean ports, and Polynesian navigation cultures. If true, Harireh combined engineering, astronomy, and commerce into a unified urban system, designed specifically for survival and control in one of the harshest trade environments on Earth. What do you think really caused the sudden collapse of Harireh? Environmental disaster, hidden engineering failure, or something historians still haven't discovered? Share your theory in the comments below. In the burning plains of Upper Mesopotamia, where summer temperatures can exceed 45 degrees Celsius, the ruins of Harran hide one of the strangest engineering mysteries of the ancient world. A city over 4,000 years old survived in a near-desert environment using technologies that modern scientists are still trying to fully understand, including houses that functioned like natural air conditioners centuries before electricity even existed. Harran has been mentioned in Assyrian records, Roman texts, and even biblical sources for thousands of years, but large-scale archaeological excavations only intensified during the 19th and 20th centuries. Researchers uncovered collapsed observatories, advanced irrigation channels, massive mud brick fortifications, and the famous conical beehive houses that turned Harran into one of the most scientifically puzzling settlements in Mesopotamia. What shocked archaeologists most was not simply the age of the city, but how technologically optimized it appeared for survival. Harran sits in one of the harshest climate zones in the Fertile Crescent. Average summer temperatures regularly climb above 40 degrees Celsius, while humidity remains extremely low. Under these conditions, ancient urban settlements normally struggled to maintain stable populations, yet Harran remained inhabited for over 4 millennia. Satellite studies and excavation data reveal that the city was designed with unusually narrow streets and densely clustered structures. Modern thermal simulations suggest these layouts reduced direct solar exposure and created pressure-driven airflow corridors similar to cooling systems used in modern passive architecture. Researchers comparing Harran to Roman desert forts found that Harran's street orientation produced significantly lower daytime ground temperatures. Some estimates suggest shaded alley temperatures could drop by 5-7 degrees Celsius compared to open terrain nearby. This means the entire city may have functioned as a giant climate control machine. The most mysterious structures in Harran are its iconic beehive houses, cone-shaped mud brick buildings that still survive today. At first glance, they appear primitive, but engineers studying them discovered something astonishing. The tall conical domes naturally force hot air upward, while cooler air remains trapped below. This creates a continuous convection cycle without fans, vents, or mechanical systems. In modern engineering, the same principle is used in passive cooling towers and eco-friendly sustainable buildings. Inside some beehive houses, researchers recorded interior temperatures up to 10-15 degrees Celsius, cooler than the outside desert air during peak summer heat. That is an enormous thermal difference. The secret appears to come from 3 combined engineering principles. First, the cone geometry minimizes direct sunlight exposure during most hours of the day. Unlike flat roofs that absorb heat continuously, the curved surface constantly shifts the angle of solar impact. Second, the mud brick walls act as thermal batteries. Because mud brick has high thermal mass, heat penetrates extremely slowly. During the day, the walls absorb heat gradually instead of instantly transferring it inside. At night, when desert temperatures drop sharply, the stored heat escapes back outward. Third, tiny openings near the top of the dome create pressure-based airflow. Hot air naturally rises and exits through upper vents, pulling cooler air inward from lower sections. Modern climate engineers have compared Harran's beehive houses to experimental sustainable buildings in the Middle East, and even NASA-inspired habitat concepts for Mars, where passive temperature regulation is considered essential due to limited energy resources. What makes the mystery even deeper is the precision of the design. The angles of many domes are surprisingly consistent, despite being built centuries apart. Some archaeologists believe Harran's builders possessed inherited architectural formulas passed down through generations, formulas optimized through long-term environmental observation. Even today, many modern concrete houses in the same region perform worse thermally than these ancient mud brick structures. Harran was not only a trade city, it was also one of the oldest scientific centers in Mesopotamia. Historical records describe Harran as a major hub of astronomy, mathematics, medicine, and philosophy during the late Babylonian and early Islamic periods. Scholars from across the region travelled there to study celestial movements and translate Greek scientific texts into Arabic. But some discoveries suggest Harran's astronomical knowledge may have been even older. Fragments of star charts and astronomical records linked to Harran show observations of lunar cycles and planetary motion with remarkable precision. Certain calculations related to eclipses appear unexpectedly accurate for a civilization without telescopes. Some historians believe Harran inherited observational data accumulated over centuries from earlier Mesopotamian cultures. Others argue the city may have operated continuous sky monitoring traditions for generations. The biggest mystery is data continuity. How did ancient scholars preserve highly accurate astronomical measurements across hundreds of years without losing critical information? Because even small observational errors would compound over time. Yet several reconstructed lunar calculations associated with Harran remain surprisingly close to modern astronomical models. Most ancient mud brick cities eventually collapsed due to erosion, moisture, or seismic damage. Harran should have disappeared long ago, but parts of its structures still stand after thousands of years under extreme desert conditions. Material scientists examining Harran's bricks discovered microscopic organic fibers mixed with clay and mineral sediments. Some samples also showed crystalline salt formations that developed naturally over centuries. This created an effect similar to geological stabilization. Instead of weakening rapidly, certain walls appear to have gradually hardened over time due to repeated heating, drying, and mineral crystallization cycles. Researchers have compared this process to natural ceramic transformation. Some sections of Harran's surviving walls demonstrate compression resistance far beyond what modern unfired mud brick would normally achieve. In comparison, many modern reinforced concrete structures begin serious deterioration within 5,100 years, yet Harran's earthen architecture survived millennia. That raises a disturbing possibility. Ancient builders may have understood local environmental chemistry far better than we assume. No ancient city could survive for thousands of years without reliable water, and yet Harran existed in an environment with limited rainfall and brutal evaporation rates. Excavations uncovered complex underground water channels, wells, and carefully graded irrigation systems extending beneath parts of the city. Some channels maintained slope variations of only a few centimeters across long distances, a level of hydraulic precision difficult to achieve without advanced surveying techniques. Hydrologists studying the ruins believe Harran's inhabitants possessed extensive knowledge of underground water behavior and seasonal flow patterns. Some theories suggest they intentionally designed portions of the city above shallow groundwater zones to maximize moisture retention in nearby agricultural land. The engineering resembles systems later seen in Persian qanats and Roman hydraulic infrastructure, though parts of Harran may predate both. Harran was one of the major centers devoted to Sin, the Mesopotamian moon god, but the city's religious architecture may have also functioned as astronomical instruments. Several surviving structural alignments appear connected to lunar rising positions and long-duration moon cycles. Some researchers suspect the orientation of sacred buildings corresponded with the 18.6-year lunar nodal cycle, an astronomical phenomenon requiring decades of observation to identify accurately. That level of tracking would demand organized scientific observation across generations. If true, Harran's priests may have acted not only as religious leaders, but as highly trained astronomers preserving complex celestial data long before modern science existed. Do you think ancient civilizations like Harran understood sustainable climate engineering better than we do today? Share your thoughts and theories in the comments below. Inside the ancient temple complex of Lepakshi in southern India, a massive stone pillar hangs slightly above the ground without fully touching it. For nearly 500 years, the structure surrounding it has remained standing, and modern engineers still cannot fully explain why the temple works at all. The temple was constructed during the 16th century under the Vijayanagara Empire, but Lepakshi became globally famous during the British colonial era, when engineers discovered that one of its giant granite pillars could not fully touch the floor. Attempts to study the pillar reportedly caused slight displacement inside the structure itself, transforming the site into one of the most mysterious engineering puzzles in India. The most famous mystery inside Lepakshi is the so-called hanging pillar. Out of nearly 70 giant granite columns supporting the Virabhadra temple, one pillar appears partially suspended above the ground, allowing visitors to slide cloth or paper beneath it. At first, this seems like a simple optical illusion caused by uneven flooring, but structural analysis suggests something much more complicated. Despite not transferring weight conventionally into the foundation below, the pillar still appears to participate in supporting the enormous stone ceiling above it. In modern engineering, buildings rely on direct vertical load transfer, where gravity moves through columns into the ground. Yet Lepakshi seems to redistribute force sideways through interconnected stone beams and compression balancing. This becomes even more difficult to explain considering the material involved. Granite possesses immense compressive strength, ranging between roughly 130 and 250 megapascals, but it is also highly brittle under tension. A small error during construction should have created cracks or structural collapse centuries ago. Instead, the temple has survived almost 500 years of monsoon humidity, thermal expansion, erosion, and seismic vibration. British engineers reportedly attempted to move the pillar during the colonial era to understand its mechanism, but local accounts claim the ceiling shifted slightly almost immediately afterward. Whether exaggerated or not, the incident reinforced the belief that the hanging pillar was not decorative, but part of a precisely balanced mechanical system. Even modern computer simulations still struggle to fully explain how the load distribution inside Lepakshi functions without conventional anchoring methods. Another major mystery involves the transportation and placement of the enormous granite stones used throughout the temple complex. Some beams inside Lepakshi stretch beyond 7 meters in length and weigh several tons, yet the surrounding region lacks nearby quarry sources capable of explaining every stone used in construction. This raises one of the oldest unanswered questions in ancient engineering. How were these stones moved with such precision? The builders of the Vijayanagara Empire had no hydraulic cranes, steel pulleys, diesel machinery, or modern lifting systems, yet they positioned gigantic stone masses accurately enough to preserve structural balance for centuries. Researchers believe ancient engineers may have relied on combinations of earthen ramps, wooden rollers, counterweight systems, and coordinated labor forces. Similar theories are proposed for the Egyptian pyramids and the colossal megaliths of Baalbek in Lebanon. However, no experimental archaeology project has successfully reproduced the exact scale and precision of Lepakshi using only period-accurate technology. Some granite joints within the temple are fitted so tightly that even blade-width gaps are difficult to detect. Precision at that level becomes exponentially harder when dealing with stones weighing multiple tons because microscopic alignment errors increase dramatically under immense pressure. The mystery is therefore not simply how the stones were transported, but how they were positioned with enough accuracy to maintain long-term mechanical equilibrium without steel reinforcement or modern surveying equipment. Lepakshi also presents a major puzzle in terms of structural survival. Southern India experiences occasional seismic activity, seasonal flooding, heat expansion, and gradual geological shifting, yet much of the temple remains remarkably intact after centuries of environmental stress. Modern earthquake-resistant architecture often relies on flexible foundations, steel reinforcement systems, and shock-absorbing technologies to dissipate kinetic energy. Lepakshi possesses none of these recognizable modern systems, yet its structure continues to resist collapse. Some researchers believe the temple may use primitive forms of vibration redistribution through interconnected stone geometry. Instead of resisting force directly, the structure may redirect stress across multiple pillars and beams, reducing concentrated failure points throughout the building. This concept resembles the earthquake-resistant stonework seen in Incan architecture at Machu Picchu and Cusco, where precisely cut stones absorb movement without catastrophic collapse. In both cases, ancient civilizations appear to have understood stress behavior at a surprisingly advanced level that is difficult to explain purely through trial and error. Some engineers even suspect the hanging pillar itself may help redistribute force through micro-adjustments within the structure. If that interpretation is correct, Lepakshi would represent not merely a religious monument, but a sophisticated experiment in mechanical force management centuries ahead of its time. Among all the mysteries surrounding Lepakshi, the most scientifically puzzling may be the survival of its ceiling paintings. The temple contains some of the finest mural artwork from the Vijayanagara period, and many pigments remain visible and vibrant despite nearly 500 years of exposure to oxidation, humidity, smoke, dust, biological decay, and extreme heat. Under ordinary environmental conditions, ancient pigments gradually deteriorate as ultraviolet radiation breaks molecular bonds. Moisture encourages fungal growth, and thermal expansion causes cracking and separation from the surface beneath. Yet large sections of the Lepakshi murals still preserve deep reds, earthy yellows, blacks, whites, and muted blues with extraordinary clarity. Scientific analysis suggests many of the pigments were created using naturally occurring minerals ground into ultrafine powders. Red colours may have contained iron oxide compounds similar to hematite, while yellow tones likely came from ochre rich in hydrated iron minerals. Carbon black pigments may have been produced from soot residues created during controlled combustion. However, the greatest mystery lies not in the pigments themselves, but in the binding medium used to preserve them. Researchers believe Vijayanagara artisans mixed the mineral powders with organic substances capable of penetrating microscopic pores within the stone surface. Instead of resting on top of the ceiling like ordinary paint, parts of the pigment appear chemically integrated into the material itself. This creates a preservation mechanism surprisingly similar to modern mineral staining techniques used in industrial construction. Some conservation scientists compare Lepakshi's murals to the Roman frescoes of Pompeii, where pigments fused into wet plaster through chemical carbonation. Yet the comparison makes the mystery even stranger because Lepakshi exists in a far harsher tropical climate than the relatively dry Mediterranean environment surrounding Pompeii. The survival rate becomes even more astonishing when compared with many medieval European church paintings that faded far more severely despite surviving for shorter periods. Another unexplained detail involves the smooth preparation layers beneath certain mural sections, suggesting advanced polishing or mineral treatment techniques before painting even began. The exact organic formula used by Vijayanagara craftsmen has never been completely reconstructed, meaning part of the technology responsible for preserving these colours across half a millennium may have been permanently lost. Near the temple lies another strange anomaly, a giant footprint-shaped depression carved into stone measuring more than 1 meter in length. Local legends claim the footprint belongs to Hanuman, the monkey deity associated with the Ramayana epic, while others believe it marks the step of a divine giant. But the real mystery is the water contained inside it. Even during intense heat and dry weather, the footprint often remains filled with moisture or standing water. Some researchers argue that underground capillary seepage slowly feeds the depression from below, while others believe the footprint may have been intentionally engineered to collect rainwater or condensation. No explanation has been universally accepted. Whether natural or artificially modified, the feature contributes to Lepakshi's growing reputation as a place where mythology and unexplained engineering continuously overlap. Chan Chan Archaeological Zone emerged from the Peruvian desert only a few kilometers from modern Trujillo, where archaeologists in the 19th and early 20th centuries began uncovering massive adobe walls buried beneath centuries of wind-blown sand. What they discovered was shocking. An ancient city covering more than 20 square kilometers, making Chan Chan the largest adobe city ever built on Earth. Constructed by the Chimu civilization around 900 AD, and later conquered by the Inca around 1470, the city should not have survived at all. The northern coast of Peru is repeatedly devastated by El Niño storms capable of dissolving mud brick architecture within days. Yet enormous sections of Chan Chan still stand after more than 700 years, and the engineering methods behind that survival remain one of archaeology's greatest unsolved mysteries. The first thing that confuses researchers is the material itself. Chan Chan was built almost entirely from adobe, sun-dried mud bricks generally considered weak compared to stone. In most environments, adobe erodes rapidly under heavy rain. However, some walls at Chan Chan still rise over 9 meters high with carvings that remain sharply visible. Modern analysis found that the Chimu likely mixed clay with crushed shell, mineral-rich sand, organic fibers, and fine gravel in highly specific ratios. Certain samples even display unusually dense internal bonding patterns, resembling primitive geopolymer reactions. Engineers have attempted to recreate similar mixtures, but many replicas deteriorate far faster than the originals. This has led some researchers to believe the Chimu possessed a lost formula for waterproof or self-stabilizing adobe centuries ahead of its time. The scale of construction creates even more questions. Experts estimate millions of adobe bricks were required to build Chan Chan's palaces, ceremonial compounds, storage complexes, and defensive walls. Unlike civilizations that relied on wheeled transport or iron tools, the Chimu built this enormous city using basic hand tools and human labor. Yet the walls maintain strikingly straight alignments over long distances. Some corridors extend for hundreds of meters with only minimal deviation, suggesting sophisticated surveying methods. Archaeologists suspect the use of stretched chord measurement systems, standardized molds, and geometric planning techniques comparable in precision to systems used in ancient Egypt or Rome. One of the strangest mysteries involves the relief carvings covering the city's walls. Endless repeating patterns of fish, pelicans, waves, and fishing nets dominate the architecture. The carvings appear almost machine-made in their consistency. In several compounds, the same symbols repeat with nearly identical spacing across massive surfaces. Researchers still debate how such precision was maintained on fragile wet adobe before drying. Some believe the Chimu may have used reusable carved molds pressed directly into the walls, effectively creating a primitive form of industrial architectural replication. If true, Chan Chan may represent one of the earliest large-scale examples of standardized modular design in the ancient Americas. The city's urban layout is equally mysterious. Chan Chan was divided into enormous enclosed compounds, known as ciudadelas, each functioning almost like a self-contained administrative fortress. Inside were ceremonial plazas, burial platforms, water reservoirs, warehouses, kitchens, and labyrinth-like passageways. Many entrances were deliberately narrow and designed to restrict movement. Some corridors force visitors through multiple sharp turns before reaching central courtyards, creating what modern architects compare to controlled access security systems. This suggests the Chimu elite carefully regulated the flow of goods, people, and information. Researchers are especially fascinated by the storage systems. Thousands of niches line the walls of storage rooms throughout the city. Some archaeologists estimate that Chan once managed enough resources to support a population exceeding 30,000 people. The organization resembles a centralized economic machine rather than a traditional city. In some ways, it has been compared to the logistical complexity of later imperial capitals such as Forbidden City or even modern warehouse distribution systems. Water engineering at Chan remains one of its most advanced and poorly understood achievements. The Chimu built extensive canal systems that diverted water from the Moche River across desert terrain into the city. Several canals maintained extremely precise gradients over long distances, allowing stable water flow without destroying the channel walls through erosion. Hydrologists studying the site found some slopes accurate within fractions of a degree. Precision difficult to achieve even with basic modern surveying equipment. Similar hydraulic sophistication is often associated with Roman aqueducts, yet the Chimu developed their systems independently on another continent. The desert climate should have made large-scale urban survival nearly impossible. Northern coastal Peru receives minimal rainfall, while temperatures and humidity fluctuate dramatically. Yet Chan appears designed to manipulate microclimates. Thick adobe walls absorb heat during the day and release it slowly at night, stabilizing interior temperatures. Narrow corridors reduce direct sunlight exposure while channeling cool ocean air through compounds. Some rooms maintain noticeably cooler temperatures even today. Modern architects studying passive climate engineering have compared aspects of Chan's thermal regulation to Persian yakhchals and Middle Eastern wind tower systems. Another unexplained feature is the city's unusual acoustics. Certain ceremonial corridors amplify footsteps and echoes in ways that feel intentional. In some compounds, whispers can travel unexpectedly far along narrow passageways. Archaeologists believe the Chimu may have deliberately engineered sound effects for rituals or political ceremonies, similar to acoustic phenomena found at Chichen Itza, where echoes mimic the call of the sacred Quetzal bird. If intentional, this would mean the Chimu understood complex architectural acoustics centuries before formal acoustic science existed. The biggest threat to Chan may have also shaped its engineering, El Niño. Geological evidence suggests massive flooding events repeatedly struck the region during the city's occupation. These storms could transform the desert into a destructive mud basin within days. Some researchers believe the Chimu constantly repaired and resurfaced walls using protective coatings now lost to time. Others argue they developed drainage systems and sacrificial outer layers designed specifically to absorb weather damage while preserving structural cores underneath. Certain walls show multiple construction layers, almost like engineered protective shells added over generations. Archaeologists also discovered evidence of one of the darkest rituals in ancient American history near Chan. In 2018, researchers confirmed the remains of more than 140 sacrificed children and over 200 llamas at nearby Huanchaquito Las Lamas. The children, estimated to be between 5 and 14 years old, showed cut marks across the chest consistent with ritual heart extraction. DNA analysis revealed they came from different regions of the Chimu kingdom, suggesting a massive organized state ritual rather than isolated sacrifice. Many scholars believe catastrophic El Niño floods triggered the ceremony as an attempt to appease supernatural forces controlling weather and the sea. Do you think the Chimu discovered an ancient engineering technique that modern science still cannot fully reproduce? Share your thoughts and theories in the comments below. Buried beneath the rainforests of Chiapas, Mexico, the walls of Bonampak still glow with colors painted more than 1,200 years ago. Sealed inside a small Maya structure known as the Temple of the Murals, these paintings are so detailed, vivid, and technically advanced that many archaeologists consider them one of the greatest unsolved artistic mysteries of the ancient world. The site remained swallowed by jungle until the early 20th century, when Lacandan Maya guys led photographer Giles Healy to the ruins in 1946. What he found inside shocked researchers worldwide. Unlike the faded carvings of many Maya cities, Bonampak preserved entire walls covered in complex scenes of war, ritual, music, sacrifice, and royal ceremony. More than 400 human figures appear across 3 chambers, painted with remarkable realism and motion. Even today, many sections still retain strong traces of blue, red, yellow, black, and green pigments despite surviving for over 12 centuries inside one of the harshest climates on Earth. What makes Bonampak mysterious is not simply the artwork itself, it is the level of chemical knowledge, architectural control, and artistic sophistication required to create something this durable in a tropical rainforest, where humidity often exceeds 90%. Entire modern murals decay faster. The most famous mystery surrounding Bonampak is the extraordinary preservation of its pigments, especially the legendary Maya blue. Scientists have spent decades trying to fully understand why this color resists destruction so effectively. Unlike ordinary ancient dyes, Maya blue is not just paint, it is a hybrid nanomaterial created by combining indigo dye with a rare clay mineral called palygorskite. Laboratory analysis revealed that the pigment possesses an unusually stable molecular structure. It resists acids, humidity, biological decay, and even chemical solvents that normally destroy ancient paints. Researchers subjected samples to nitric acid and extreme environmental testing, yet the pigment remained stable. Some chemists compare its durability to advanced modern industrial pigments. The mystery is how the Maya achieved this without modern chemistry. Experimental archaeology suggests the mixture required carefully controlled heating between roughly 150 and 200 degrees Celsius. If the temperature varied too much, the molecular bond would fail, yet the Maya had no thermometers, industrial kilns, or modern laboratory equipment. Even more puzzling is that the pigment appears across multiple sacred Maya sites over hundreds of years with remarkable consistency. This suggests a standardized production process sophisticated enough to maintain nearly identical chemical properties over generations. Some historians believe the recipe may have been controlled by elite priestly classes and treated as sacred knowledge. Compared to Egyptian blue, one of the earliest synthetic pigments in history, Maya blue demonstrates even greater resistance to tropical moisture. While many Roman and Egyptian wall paintings faded dramatically over time, Bonampak's colors survived inside dense rainforest conditions that should have accelerated decay. The greatest mystery at Bonampak may not be the colors themselves, but the astonishing artistic depth of the murals. Unlike most ancient American wall art, Bonampak's figures possess movement, layered composition, emotional expression, and spatial complexity that seem centuries ahead of their era. The murals depict musicians turning their bodies in motion, nobles interacting in crowded ceremonial scenes, and warriors collapsing in battle with anatomically convincing poses. Faces display fear, exhaustion, triumph, and pain. Some scenes contain overlapping figures arranged in ways that create visual depth rarely seen in pre-Columbian art. Art historians often compare this sophistication to later Renaissance fresco traditions in Europe. Yet Bonampak predates the Italian Renaissance by nearly 700 years. What makes this even stranger is the technical execution beneath the visible paint. Microscopic studies show that Maya artists applied pigments onto extremely smooth lime plaster surfaces using multiple thin layers. In some sections, painters adjusted pigment density to create subtle shading effects, producing volume and depth rather than flat symbolic imagery. This required extraordinary timing. Fresco-style painting demands application while plaster retains precise moisture levels. If painters worked too early, pigments would bleed. Too late, and the surface would reject the paint entirely. Bonampak's murals reveal almost no large-scale technical failures despite covering entire chambers. Some researchers believe Maya artists may have used grid systems or geometric planning methods hidden beneath the compositions. Infrared imaging has detected faint preliminary sketching beneath certain painted layers, suggesting organized planning rather than spontaneous decoration. Yet no surviving Maya manuals explain how these artists achieved such consistent proportions and perspective-like arrangements. The visual complexity becomes even more astonishing considering the lighting conditions. Bonampak's rooms were extremely dark. Ancient artists likely painted much of the work under torchlight or limited daylight entering narrow doorways. Flickering flames would distort color perception and shadow balance, making precision work extraordinarily difficult. Even modern mural restorers working under electric lighting struggle to reproduce comparable results on wet plaster at such scale. Some scholars argue that Bonampak represents the peak of a lost Maya painting tradition that largely disappeared after the collapse of classic Maya civilization in the 9th century. Others suggest the murals hint at an artistic knowledge system far more advanced than historians once believed possible in the Americas. Before Bonampak's discovery, many early researchers portrayed the Maya as peaceful astronomers and mathematicians. The murals shattered that image completely. One chamber depicts violent warfare with shocking realism. Captured prisoners kneel naked before victorious nobles, while blood flows from mutilated hands and torn fingernails. Warriors wear jaguar pelts, elaborate feathered headdresses, and standardized weapons. Battle scenes show organized military structure rather than chaotic tribal fighting. This transformed scholarly understanding of Maya politics. Archaeologists began recognizing that many Maya city-states engaged in highly organized warfare, political intimidation, and ritualized violence. The murals also reveal remarkable observational accuracy. Human musculature, body claps, and movement appear surprisingly realistic compared to many other ancient war depictions. Some historians wonder whether Maya artists directly witnessed the battles they painted or used detailed sketching techniques previously unknown in the region. Bonampak's survival itself may be one of the site's greatest enigmas. Tropical rainforests are among the most destructive environments for ancient art. Constant moisture encourages fungal growth, salt migration, bacterial activity, and mineral breakdown. In many tropical archaeological sites, painted surfaces vanish within centuries. Yet Bonampak endured for over 1,200 years. Scientists believe the architecture accidentally created a stable microclimate. Thick limestone walls reduced rapid temperature shifts, while the interior chambers remained protected from direct sunlight and rainfall. Limited airflow may also have slowed oxidation reactions that normally destroy pigments. However, these explanations remain incomplete. Conservation teams discovered traces of thin organic coatings on some mural surfaces, possibly derived from plant resins or natural binders. If true, the Maya may have intentionally engineered protective sealants centuries before modern varnish chemistry. No one fully understands the formula. Many researchers believe the murals carried deeper cosmological meaning beyond simple historical recording. The famous blue pigment was closely associated with water, sacrifice, gods, and the heavens throughout Maya civilization. At sites such as Chichen Itza, sacrificial victims thrown into sacred cenotes were sometimes coated in blue pigment before rituals. This suggests Maya blue held religious significance far beyond aesthetics. Certain Bonampak scenes also appear arranged according to ritual hierarchy and celestial symbolism. Some scholars argue the mural chambers themselves may have functioned as symbolic cosmic spaces representing divine order, warfare, and royal legitimacy. If true, Bonampak was not simply art, it was sacred technology, a combination of chemistry, architecture, religion, and political propaganda fused into a single immersive environment. Do you think the Maya truly discovered a lost chemical technology far ahead of its time? Or are the murals of Bonampak simply the last surviving piece of an ancient knowledge system we still don't fully understand? Let me know your thoughts in the comments below. Rising directly from a limestone hill above the Zagros Mountains of western Iran, Falak-ol-Aflak Castle has survived earthquakes, invasions, floods, and wars for more than 1,700 years. Even today, engineers still debate how a fortress built during the Sassanid era could endure in one of the most seismically active regions of the Middle East, while preserving walls several meters thick almost intact. The fortress was first systematically studied by modern archaeologists during surveys in the early 20th century, although local populations had known the structure for centuries. Excavations later revealed hidden tunnels, advanced water systems, unusual ventilation shafts, and construction materials whose durability continues to puzzle material scientists today. Unlike many ancient fortresses that were constructed on prepared foundations, Falak-ol-Aflak appears partially fused with the hill beneath it. Large sections of the structure were built directly onto natural bedrock, with almost no visible separation between the artificial and natural layers. This technique dramatically increased stability. Modern structural studies show that buildings anchored directly into bedrock distribute seismic energy more effectively than structures resting on softer sediment. That matters because Lorestan province lies close to several active fault systems capable of generating earthquakes above magnitude 6. The Sassanids somehow selected one of the most geologically stable points in the valley centuries before modern geology existed. The hill itself consists of dense limestone formations, resistant to erosion and capable of supporting extreme weight loads. Some researchers compare this strategy to the cliff integration seen at Machu Picchu or the mountain-cut foundations of Masada. But Falak-ol-Aflak differs because its builders combined natural terrain with defensive military engineering on a far larger enclosed scale. The fortress originally covered nearly 5,300 square meters and contained 12 towers connected by massive defensive walls. The positioning created overlapping lines of sight across the Khorramabad Valley, allowing defenders to monitor movement from nearly every direction. What remains unexplained is the precision of the integration. Some lower sections appear almost carved into the hill itself, suggesting advanced stoneworking methods or extremely long construction phases requiring remarkable planning coordination. Summer temperatures in western Iran can exceed 40 degrees Celsius, yet parts of the fortress remain significantly cooler even today. Inside the structure, archaeologists discovered networks of narrow corridors, vertical shafts, and interconnected chambers designed to control airflow. Hot air naturally rises through upper vents, while cooler air circulates through lower passageways, creating continuous passive ventilation. This resembles later Persian windcatcher systems known as badgirs. but the fortress design appears older and more militarized. Unlike open urban cooling towers, these systems were hidden inside thick defensive walls. Researchers comparing airflow models found that some chambers maintain temperatures several degrees below the exterior environment without mechanical assistance. Similar principles appear in Persian Qanat systems and even Roman hypocaust engineering, yet Falak-ol-Aflak combined climate control with military architecture in ways rarely seen elsewhere. The exact efficiency of the system remains difficult to reproduce because some internal tunnels collapsed centuries ago. Modern engineers believe the fortress may once have contained a far more extensive underground circulation network than what survives today. One of the greatest mysteries beneath the fortress involves its underground passages. Surveys using ground-penetrating radar revealed cavities and tunnels extending deep below the visible structure. Some likely connected the fortress to external water sources, allowing defenders to survive prolonged sieges without relying entirely on rainfall. The tunnels appear carefully angled to control water movement and drainage pressure. Cutting such passages through hard limestone without modern drilling equipment would have required enormous labour and advanced surveying accuracy. Several historians believe the underground system functioned similarly to fortified hydraulic networks found in ancient Persian desert settlements. Others argue the tunnels also served military purposes, including emergency escape routes and concealed troop movement. The most controversial theory suggests parts of the network remain undiscovered beneath modern Khorramabad itself. Because many underground sections are unstable and inaccessible, the true scale of the subterranean system is still unknown. The greatest engineering mystery of Falak-ol-Aflak is not its tunnels or ventilation system, it is the survival of its walls. For nearly 17 centuries, the fortress endured earthquakes, invasions, weather erosion, flooding, and military conflict. Arab armies, Mongol forces, regional dynasties, and modern warfare all damaged the structure, yet major sections remain standing. Some defensive walls exceed 3 meters in thickness and were constructed using large fired bricks bonded with an unusually resilient mortar mixture. Laboratory studies on surviving samples indicate the mortar contains combinations of lime, clay minerals, silica-rich compounds, and organic binding materials that improved flexibility and moisture resistance. This is where the mystery deepens. Most ancient masonry becomes brittle with age. Falak-ol-Aflak's walls, however, appear to absorb seismic stress rather than simply resisting it. Engineers studying the fortress observed micro-flexibility within certain sections of the masonry, meaning the walls can slightly shift under stress without catastrophic collapse. This principle resembles modern earthquake-resistant engineering techniques used in reinforced concrete structures today. Some researchers compare the material to Roman volcanic concrete, famous for surviving marine environments for over 2 millennia. Others point toward Persian sarouj, an ancient waterproof mortar mixture known for extreme durability. Yet the exact formula used at Falak-ol-Aflak has never been fully reconstructed. Even more puzzling is the balance between hardness and elasticity. Normally, increasing compressive strength reduces flexibility, but the fortress walls demonstrate both properties simultaneously. That combination is extraordinarily difficult to achieve, even with some modern materials. The bricks themselves also show remarkable consistency. Many were fired at temperatures estimated between 800 and 1000 degrees Celsius, creating dense ceramic-like surfaces highly resistant to moisture penetration. In some areas, erosion damaged the outer surfaces while the inner structural layers remained intact. Comparisons with nearby medieval structures reveal dramatically different survival rates. Buildings constructed centuries later collapsed entirely, while portions of Falak-ol-Aflak endured. This suggests the Sassanid builders possessed unusually advanced empirical knowledge of structural behavior, even without formal modern physics. Researchers also noticed that some walls subtly taper inward as they rise. This design lowers the center of gravity and distributes weight more efficiently during seismic activity. Similar techniques later appeared in parts of Islamic and Ottoman military architecture, but Falak-ol-Aflak may represent one of the earliest large-scale examples in the region. The fortress essentially behaves like a hybrid between rigid stone architecture and flexible seismic engineering, a concept far ahead of what most historians once assumed ancient military builders understood. The fortress dominates the Khorramabad Valley from a near-perfect observation point. From its towers, defenders could monitor trade routes, military movement, and river access across large sections of the Zagros corridor. The location also sits close to natural water resources while remaining difficult to assault directly due to steep terrain. Some archaeologists argue the site selection demonstrates advanced environmental knowledge rather than simple military instinct. The builders chose a hill resistant to erosion, naturally elevated above flood zones, and structurally stable enough to support immense masonry weight. Several tower alignments also correspond roughly with seasonal solar positions. While evidence for intentional astronomical design remains debated, the precision of the fortress layout continues to raise questions about the surveying methods available to Sassanid engineers. Do you think the builders of Falak-ol-Aflak possessed engineering knowledge far ahead of their time, or are we simply underestimating ancient civilizations? Share your thoughts and theories in the comments below. Burana Tower rises from the plains of northern Kyrgyzstan near the ruins of ancient Balasagun, once a major Silk Road city in the Chui Valley. Archaeologists first began serious excavations here in the late 19th century after Russian surveyors reported the remains of a massive medieval tower surrounded by buried walls, stone statues, and collapsed settlements. At first glance, Burana looked like just another ruined minaret from the Islamic world. But the deeper researchers dug, the stranger the site became. The tower stood in one of the most earthquake-prone regions of Central Asia, built almost entirely from baked brick over 1,000 years ago, yet it had survived while entire nearby cities disappeared. Even more disturbing was the realization that many of its engineering methods appeared centuries ahead of what historians believed medieval builders in the region were capable of achieving. Originally estimated to have stood around 45 meters tall before part of its upper section collapsed, Burana Tower was constructed during the Karakhanid period around the 10th or 11th century. Today only about 24 meters remain, yet despite losing nearly half its height, the structure continues to stand with remarkable stability. This immediately created one of the biggest mysteries surrounding the tower. How did a brick structure survive repeated seismic disasters for over a millennium in a valley known for violent earthquakes? Modern seismic engineers studying Burana noticed something unusual beneath the foundation. Unlike many rigid medieval towers that cracked catastrophically during ground movement, Burana appears to have been built on a partially flexible base system. Excavations revealed layered foundations containing clay, gravel, and compacted organic materials capable of absorbing vibration. In modern engineering, similar principles are used in base isolation systems designed to reduce earthquake damage in skyscrapers and bridges. The comparison shocked some researchers because the concept should not have existed in Central Asia 1,000 years ago. Historical records show multiple devastating earthquakes struck the region, including major seismic activity estimated above magnitude 7 in surrounding areas over the centuries. Entire settlements vanished, yet Burana endured. The tower's cylindrical design may also have contributed to its survival. Circular structures distribute seismic stress more evenly than square buildings, reducing the concentration of force at corners. This principle is now widely used in earthquake-resistant architecture. But what puzzled researchers was the precision with which the Karahanid builders implemented the geometry. Even after centuries of erosion, the tower's tilt remained surprisingly small relative to its remaining height. Survey data suggests the deviation from the vertical axis is minor compared to many surviving medieval towers worldwide. For comparison, the famous Leaning Tower of Pisa developed severe instability, partly because of uneven soil compression beneath a rigid foundation. Burana, built in an active seismic zone, somehow remained structurally coherent. Another mystery lies in the bricks themselves. Tens of thousands of baked bricks were used in the construction, many displaying an unusually consistent size and density. Maintaining such uniformity in the 10th century would have required extremely controlled kiln temperatures and standardized production techniques. Laboratory analysis of surviving samples found evidence of high-temperature firing that strengthened the ceramic structure of the bricks while minimizing cracking. Some engineers noted that certain bricks demonstrated compressive strengths, approaching weaker forms of modern concrete. This was extraordinary considering the technological limitations traditionally associated with medieval Central Asia. Researchers also discovered that many bricks retained unusually low moisture penetration, despite centuries of exposure to snow, rain, seasonal freezing, and extreme temperature changes. Some scientists suspect the clay composition may have included carefully selected mineral content that improved thermal resistance. Similar mysteries exist at other ancient sites, where builders appeared to possess advanced practical knowledge of material science long before formal chemistry existed. Roman concrete, for example, became stronger over time through chemical reactions with seawater. The mortar used in Burana presents a similar puzzle. The mortar binding the tower together remains one of the least understood elements of the structure. In some sections, the bonding material hardened to such a degree that separating individual bricks without destroying them became nearly impossible. Chemical traces suggest a mixture of lime-based compounds combined with organic additives. Certain Central Asian construction traditions involved mixing plant fibers, ash, animal products, or fermented substances into mortar to increase durability and flexibility. But Burana's formula appears unusually resilient. Many nearby medieval structures collapsed into loose debris centuries ago, while large portions of Burana's masonry remain locked together like fused stone. Equally mysterious are the decorative geometric bands spiraling around the tower. At first, they appear purely artistic, consistent with Islamic architectural traditions of the period. Yet structural analysts proposed another possibility. The repeating ridge patterns may help disperse stress across the surface during seismic vibration, functioning similarly to reinforcement rings. Modern earthquake-resistant towers often use external structural bands or segmented surfaces to reduce cracking under oscillation. Burana's builders may have unintentionally or intentionally discovered a primitive version of the same principle. The precision of the tower's construction raises even deeper questions. Medieval builders lacked lasers, computer modeling, or modern surveying equipment. Yet Burana was aligned and balanced with extraordinary accuracy. Some historians believe astronomical observation may have been used during planning. Across the ancient world, civilizations repeatedly demonstrated advanced celestial alignment skills. The Maya aligned pyramids with solar cycles. Egyptian temples tracked equinoxes. Persian observatories measured planetary motion with remarkable precision. Burana's builders may have inherited mathematical traditions traveling along Silk Road knowledge networks, connecting China, Persia, India, and the Islamic world. Surrounding the tower are dozens of ancient Balbal stone statues scattered across the site. These carved stone figures predate the Islamic structure and likely belong to older Turkic burial traditions. Their presence suggests the location may have been spiritually important long before the Karakhanids arrived. Some archaeologists believe the tower was deliberately built atop a much older sacred zone connected to pre-Islamic ritual practices. This layering of civilizations complicates the site's history. Burana may not simply represent one culture's engineering achievement, but centuries of accumulated knowledge inherited from multiple Central Asian societies. Excavations around Beycesultan uncovered further evidence that the city itself was far more advanced than once assumed. Archaeologists discovered urban planning systems, irrigation channels, workshops, and traces of long-distance trade infrastructure tied to the Silk Road economy. Historical accounts describe Beycesultan as a wealthy intellectual centre during the Karakhanid era. Yet, despite its importance, the city almost completely vanished from global historical memory after invasions, political fragmentation, and environmental decline reshaped the region. One of the greatest unanswered questions is whether Burana's survival was partly accidental or the result of intentionally advanced engineering knowledge. Medieval builders often relied on empirical learning accumulated over generations rather than formal scientific theory. Yet the combination of flexible foundations, high-strength bricks, resilient mortar, cylindrical geometry, and stress-dispersing surface patterns creates a system that resembles modern seismic engineering principles with disturbing accuracy. Do you think the survival of Burana Tower was simply incredible engineering for its time, or evidence that ancient builders understood technologies we still do not fully understand today? Share your thoughts in the comments below. On Kamer Hill in modern-day Armenia, the ruined fortress city of Teishebaini still stands like the remains of a civilization that understood engineering centuries ahead of its time. Buried beneath ash and collapsed stone, archaeologists uncovered earthquake-resistant walls, industrial-scale metal workshops, underground climate-controlled storage systems, and Iron Age alloys so precise that some researchers still debate how they were produced without advanced tools. Teishebaini was rediscovered in 1939 by Soviet archaeologist Boris Piotrovsky after local villagers repeatedly uncovered ancient pottery and burned brick fragments around Kadmir. Excavations soon revealed the destroyed capital of a late Eurasian fortress city dating to the 7th century BCE, likely destroyed around 585 BCE during the collapse of the Kingdom of Urartu. What researchers expected to find was a typical Iron Age stronghold. What they found instead looked more like a highly organized military-industrial complex. Massive wine cellars stretched beneath the citadel. Bronze armor fragments were scattered beside advanced furnaces. Entire storage chambers remain preserved under layers of fire-hardened debris. Some walls still stood after more than 2,600 years in one of the most earthquake-prone regions of Eurasia. The deeper archaeologists dug, the stranger Teishebaini became. One of the first mysteries that shocked researchers was the fortress's unusual structural durability. Armenia sits near active tectonic zones, where earthquakes have repeatedly destroyed cities throughout history. Yet large portions of Teishebaini survived long enough to remain identifiable after over 2.5 millennia. The construction methods appeared deceptively simple. Lower foundations were built from heavy volcanic stone blocks, while upper sections used thick mud bricks. But detailed analysis revealed the builders intentionally designed the lower layers to remain slightly flexible instead of perfectly rigid. Modern structural engineers noticed similarities between this technique and later anti-seismic principles used by Roman and Inca builders. Rather than resisting seismic force directly, the structure dispersed energy through uneven stone distribution and layered compression. The mud bricks themselves remained difficult to fully explain. Many contained carefully mixed volcanic ash, clay, organic fibers, and mineral compounds. Laboratory analysis showed unusual density and compression strength compared to ordinary Near Eastern mud bricks from the same era. Even more puzzling, certain defensive corridors were constructed at subtle angles that reduced stress concentration during earthquakes and possibly improved resistance against battering attacks. Some archaeologists believe the Urartians developed empirical seismic engineering through centuries of observing mountain earthquakes, long before the science of structural dynamics existed. Compared to cities like Babylon or Nineveh, Teishebaini's architecture appears less decorative but far more optimized for survival. The greatest mystery surrounding Teishebaini may be its metallurgy. Excavations uncovered enormous quantities of bronze weapons, iron tools, ceremonial shields, armor plates, horse equipment, furnace remains, slag deposits, and industrial workshops. What stunned researchers was not merely the quantity of metal objects, but the precision of their composition. During the 7th century BCE, ironworking across much of the ancient world remained inconsistent and technologically difficult. Producing durable iron required extremely high furnace temperatures, controlled oxygen flow, and advanced knowledge of carbon absorption during smelting. Most Iron Age civilizations still struggled with brittle or impure iron, yet Teishebaini appears to have mastered large-scale production. Some furnace remains suggest temperatures may have exceeded 1,200 degrees Celsius, astonishing for the era. Researchers believe the Urartians used highly specialized bellows systems and carefully engineered airflow shafts capable of maintaining unusually stable combustion conditions. This level of thermal control is comparable in principle to much later metallurgical systems. Even stranger were the bronze alloys. Trace element analysis on Urartian bronze artifacts revealed deliberate manipulation of tin, arsenic, and copper ratios to create different hardness levels depending on an object's purpose. Decorative ceremonial shields often used alloys optimized for polish and corrosion resistance, while weapons showed compositions favoring durability and impact resistance. This implies the craftsmen understood practical metallurgical chemistry through experimentation long before formal chemistry existed. Some shield engravings displayed geometric precision so consistent that archaeologists debated whether standardized measuring systems or calibrated templates were used during production. Several bronze artifacts contain symmetrical radial patterns difficult to reproduce even with simple manual tooling. Compared to Assyrian metallurgy, which heavily emphasized royal symbolism and ornamentation, Urartian metalwork at Teishebaini appears more industrial and militarized. Certain iron spearheads from the site even show carbon distribution patterns, suggesting primitive steel-like hardening techniques. If true, this would place Urartian metallurgy far ahead of what historians once believed possible for the region. The scale of production is equally mysterious. Researchers estimate the fortress maintained enough stored weaponry and metal reserves to equip thousands of soldiers. Some scholars compare Teishebaini not to a normal city, but to a permanently active military supply hub, similar in function to later Persian frontier arsenals. But perhaps the most difficult question is how such advanced metallurgical knowledge developed in a relatively isolated mountain kingdom. Unlike Egypt or Mesopotamia, Urartu lacked the enormous population base usually associated with technological specialization. Yet the kingdom somehow created one of the most sophisticated metal industries of the Iron Age. Some historians believe constant warfare accelerated innovation. Others argue the Urartians inherited lost metallurgical traditions from earlier Anatolian cultures. A few researchers even suggest that much of Urartu's technical knowledge disappeared so completely after the kingdom's collapse that later civilizations had to independently rediscover similar techniques centuries afterward. Another astonishing mystery lies beneath the fortress itself. Teishebaini contained enormous underground storage complexes filled with giant ceramic jars used for wine, oil, grain, and preserved food. Some jars stood over 1 meter tall and were partially buried underground to stabilize internal temperature. The storage system functioned with surprising efficiency. Even without modern refrigeration, The underground chambers maintained relatively stable humidity and cooler temperatures year-round. Researchers estimate the fortress could store hundreds of thousands of litres of wine simultaneously alongside massive grain reserves capable of supporting long sieges. Chemical residue analysis revealed traces of resin compounds used to slow bacterial growth inside wine containers. This suggests Eurasian brewers possessed sophisticated practical knowledge of preservation centuries before microbiology existed. Compared to ordinary Iron Age settlements, Teishebaini's logistics resemble the supply organization of much later imperial military systems. Some archaeologists believe the fortress was designed less as a city and more as a survival machine capable of functioning independently during regional collapse. Around 585 BCE, Teishebaini was destroyed in a violent attack, possibly linked to the Scythians or the Median Empire during the collapse of Urartu. But ironically, the fire itself helped preserve the city for more than 2,600 years. The extreme heat baked the mud bricks into a ceramic-like hardness, making them far more resistant to erosion over time. Organic materials buried beneath the ruins were also sealed away from oxygen, allowing archaeologists to recover rare ancient seeds, textiles, wooden objects, and preserved food remains. Many rooms appeared almost frozen in time, with weapons and tools still lying across the floors. Even today, researchers still cannot fully explain how a fortress designed for long-term survival collapsed so suddenly. Do you think Teishebaini was simply an advanced Iron Age fortress? Or evidence that ancient civilizations understood engineering far beyond what history tells us? Share your thoughts in the comments below. Beneath the blazing cliffs of southern Iran, inside the ceremonial capital of the Achaemenid Empire, stood a structure that once held one of the greatest concentrations of wealth on Earth. But the real mystery of the Persepolis treasury was never the gold, it was the engineering. Massive stone halls that resisted collapse for 2,500 years. Precision-cut masonry fitted tighter than modern concrete seams. Reliefs that survived heat, sandstorms, and earthquakes with astonishing detail. Even today, archaeologists still cannot fully explain how ancient Persian builders achieved such durability with Bronze Age technology. The ruins of Persepolis were known locally for centuries, but systematic excavation of the treasury began in the 1930s under the Oriental Institute of the University of Chicago, led by archaeologist Ernst Herzfeld and later Erich Schmidt. Excavations uncovered clay tablets, collapsed column bases, treasury halls, and evidence that the complex once stored enormous quantities of gold, silver, tribute weapons, and ceremonial artifacts from across the Persian Empire. At its peak during the 5th century BCE, the Achaemenid Empire controlled nearly 5.5 million square kilometers, stretching from Egypt to the Indus Valley. The Persepolis treasury functioned as the financial heart of this empire. Ancient Greek sources claimed Alexander the Great seized around 120,000 talents of precious metals from Persepolis after conquering the city in 330 BCE. Modern estimates vary, but some historians calculate this may have equaled more than 3,000 metric tons of silver and gold combined. The mystery is not simply the amount of wealth. It is how such an enormous economic system operated with no electricity, no digital accounting, and no rapid communication. Thousands of clay tablets discovered around Persepolis recorded worker payments, food rations, livestock transfers, and transport logistics with astonishing precision. Some tablets even track travel routes and administrative movement across hundreds of kilometers. Many historians compare this system to the logistical complexity of the Roman Empire centuries later. Yet Persepolis existed long before Rome reached its peak. The treasury appears less like a primitive vault and more like a centralized economic machine designed to manage one of the largest empires in human history. The treasury was not built like a simple storage building. Archaeological evidence shows a maze-like complex of more than 100 rooms, corridors, storage chambers, and columned halls. Some walls exceeded 5 meters in thickness. Doorways were reinforced with heavy timber and metal fittings. The layout appears intentionally confusing, forcing movement through controlled passages rather than direct routes. This has led researchers to believe the architecture itself functioned as a security mechanism. Unlike Egyptian tombs that relied on hidden chambers or traps, the Persians may have created a psychological security system based on restricted visibility, controlled access, and administrative oversight. Modern security experts sometimes compare the design logic to controlled access banking facilities or military compounds. Yet this was achieved over 2,400 years ago using only stone, timber, geometry, and human organization. One of the greatest puzzles at Persepolis is the precision of the masonry. Many limestone blocks were cut and joined so tightly that even today it is difficult to insert a knife blade between them. In some areas, the gaps measure only a few millimeters. The precision has often been compared to the stonework of Machu Picchu and Sacsayhuaman in South America, despite the civilizations being separated by oceans and thousands of years. Unlike rough Bronze Age construction found in many ancient sites, Persepolis displays evidence of highly standardized cutting and measurement. Researchers still debate the tools used. Iron tools existed in the Persian Empire, but many archaeologists argue the visible precision exceeds what simple hammer and chisel methods should easily achieve. Some blocks weigh several tons, yet were shaped with smooth edges and remarkable symmetry. Even more mysterious is the transport system. Many stones came from quarries kilometers away. Without cranes, engines, or steel machinery, Persian engineers somehow moved and positioned enormous blocks with extraordinary accuracy across uneven terrain. The treasury reveals evidence of a civilization operating at a near-industrial scale centuries before industrialization existed. Clay administrative tablets written in Elamite recorded labor forces, construction materials, and food distribution networks involving thousands of workers. Excavations suggest Persepolis employed specialized craftsmen from across the empire, including Egyptians, Babylonians, Ionians, and Anatolians. This multinational workforce may explain why the architecture combines engineering techniques from multiple civilizations. What remains difficult to explain is the speed of construction. The major treasury expansions under Darius and Xerxes were completed within only a few decades. Considering the transportation limitations of the ancient world, many engineers believe the organizational efficiency required would rival some pre-modern megaprojects of far later periods. The Persians also developed the royal road system, stretching approximately 2,700 kilometers. Herodotus described mounted couriers capable of transferring messages across the empire with astonishing speed. Some historians believe this communication network was essential to managing treasury logistics, taxation, and tribute flow. Despite storing unimaginable wealth, archaeologists found surprisingly little evidence of elaborate physical defense systems inside the treasury itself. There are no obvious mechanical traps, no hidden vault doors comparable to later medieval fortresses, and few indications of massive military fortification within the complex. This has led to a controversial theory. The Persians may have relied less on physical barriers and more on centralized administrative control. Access to wealth was likely controlled through bureaucratic systems, specialized guards, restricted movement, and carefully organized storage sectors. In other words, the greatest security technology of Persepolis may not have been mechanical at all. It may have been information control and state organization, concepts normally associated with far more modern governments. Perhaps the most difficult mystery to explain is why so much of Persepolis survived at all. Southern Iran experiences extreme environmental stress. Summer temperatures can exceed 40 degrees Celsius. The region faces thermal expansion between hot days and cold nights, seasonal winds carrying abrasive sand particles, and occasional seismic activity. Over centuries, these conditions should have severely degraded exposed stone surfaces. Yet many relief carvings inside the treasury still preserve astonishingly fine details. Facial outlines, robe folds, inscriptions, and ceremonial symbols remain visible after more than 2,500 years of exposure. Modern geological studies suggest the Persians deliberately selected high-quality grey limestone with unusually dense structural composition. But material quality alone does not fully explain the preservation. Researchers suspect Persian builders may also have used advanced surface finishing methods or mineral-based protective treatments now lost to history. Some archaeologists point to microscopic polishing patterns on certain surfaces, suggesting intentional abrasion-resistant finishing. Others believe natural mineral reactions formed protective crusts over time. However, no consensus exists. The mystery becomes even greater when compared to other ancient sites. Large sections of limestone monuments in Egypt suffered far heavier erosion over shorter periods. Many medieval stone structures across Europe deteriorated faster despite being younger. Yet parts of Persepolis retained structural integrity across 2.5 millennia. The column bases are equally remarkable. Several survived major fires during Alexander's invasion, thermal shock, earthquakes, and centuries of abandonment. Some engineers compare this resilience to the durability mysteries of Roman pozzolanic concrete, which still survives in Mediterranean seawater after 2,000 years. Even the relief depth appears intentionally engineered. Certain carvings were cut shallow enough to reduce fracture stress, but deep enough to preserve visibility under harsh sunlight. This suggests Persian artisans may have understood long-term weathering behavior at a surprisingly advanced level. Persepolis may have been designed as a massive tool of imperial intimidation. Envoys from dozens of nations had to pass through giant stairways, enormous stone columns, and perfectly symmetrical corridors before reaching the treasury. Relief showing different peoples bringing tribute to the Persian king made the entire complex feel like a carefully staged display of power. Many historians believe this was a form of ancient psychological engineering, where architecture itself was used to overwhelm perception and reinforce imperial authority. Pasargadae was discovered in the Murghab Plain of southern Iran, nearly 130 kilometers northeast of modern Shiraz. Archaeologists identified the site as the first capital of the Achaemenid Empire after European expeditions in the 19th century compared the ruins with ancient Greek records, describing the city built by Cyrus the Great around 550 BCE. What they found was not just an ancient capital, but a place filled with engineering mysteries that still challenge historians and structural experts today. The first shock came from the city's layout. Unlike most fortified capitals of the ancient world, Pasargadae was built with a strangely open design spread across nearly 160 hectares. Massive stone palaces, gardens, water channels, and ceremonial spaces were arranged with geometric precision across the plain. Modern satellite analysis revealed that several structures align closely with solar movement and cardinal directions, suggesting the builders used advanced surveying methods thousands of years before modern instruments existed. One of the greatest mysteries surrounds the royal gardens of Pasargadae, believed to be the earliest known example of the Persian paradise garden. Archaeologists uncovered a network of limestone water channels cut with astonishing accuracy. Some channels maintain gradients so slight that the difference is only a few millimeters per meter, yet they were capable of distributing water evenly across the entire complex. For comparison, Roman hydraulic gardens with similar precision would not appear until centuries later. Engineers studying the site found that the Persians had already mastered controlled water flow, pressure regulation, and irrigation planning during the 6th century BCE. In an arid environment where summer temperatures can exceed 40 degrees Celsius, this system transformed dry land into a functioning artificial oasis. The channels themselves present another mystery. Many were carved directly into hard limestone with surfaces unusually smooth for the Iron Age. Traditional bronze and iron tools normally leave rough extraction marks, but parts of Pasargadae's channels appear almost machine-polished. Experimental archaeologists attempting to replicate these cuts using period tools required enormous labour and still failed to achieve the same consistency. Even more puzzling is the stonework throughout the city. Several palace foundations contain limestone blocks weighing multiple tons fitted together so tightly that modern researchers struggle to insert a blade between them. Some cuts display nearly perfect right angles and flat surfaces over long distances. Historians often compare this precision to the masonry seen at Machu Picchu or certain structures in ancient Egypt, despite those civilizations being separated by oceans and thousands of years. The similarities raise difficult questions about how multiple ancient societies achieved highly advanced stone engineering with supposedly primitive tools. At the center of Pasargadae stands the most famous structure of all, Tomb of Cyrus. Built more than 2,500 years ago, the tomb has survived earthquakes, invasions, weather erosion, and even deliberate destruction attempts. Yet much of the structure remains intact. Modern structural engineers studying the tomb discovered something remarkable. The monument's step foundation appears designed to disperse seismic energy rather than resist it rigidly. The layered platform allows slight movement during ground vibrations, reducing the risk of collapse. Some experts compare this concept to modern seismic base isolation systems used in earthquake-resistant skyscrapers. The stone blocks were also connected using swallowtail-shaped metal clamps. Although most metal components disappeared long ago due to corrosion or looting, their cut sockets remain visible. This technique allowed the blocks to shift slightly during seismic activity without separating completely. Similar anti-seismic engineering would later appear in some Greek and Roman structures, but Pasargadae predates many of them. Another unresolved mystery involves transportation. Some stones used at Pasargadae originated kilometers away from the construction site. Moving multi-ton limestone blocks across uneven terrain without modern cranes, steel tools, or wheeled heavy machinery would have required extraordinary coordination. Researchers proposed theories involving sledges, rollers, mud lubrication, and large labor forces, yet no definitive evidence explains how the Persians achieved such accuracy after transport. Even small alignment errors could have ruined the geometric precision visible throughout the city. Despite this, many blocks were positioned with astonishing exactness. The city's columns present another technical anomaly. Pasargadae combines architectural influences from Mesopotamia, Anatolia, Egypt, and early Greek styles in ways historians did not expect from the period. Some column bases resemble Ionian Greek forms, while certain relief techniques echo Assyrian craftsmanship. This mixture suggests that Cyrus may have assembled artisans and engineers from across conquered territories into a single imperial construction project. If true, Pasargadae may represent one of the earliest examples of large-scale international engineering collaboration in human history. Yet perhaps the strangest mystery is how advanced the city appears compared to surrounding civilizations of its time. Around the mid-6th century BCE, much of the world still relied on relatively simple urban planning, limited hydraulic systems, and localized architectural traditions. Pasargadae instead demonstrates coordinated geometry, engineered irrigation, earthquake-resistant foundations, and multinational design principles on a massive scale. Archaeologists also discovered evidence suggesting the gardens were not merely decorative. Botanical analysis indicates the Persians imported plant species from different climate zones across the empire. Maintaining such vegetation in Iran's harsh environment would have required continuous water management and sophisticated agricultural planning. Some researchers believe the city functioned as a political symbol designed to demonstrate imperial control over both nature and engineering. In this interpretation, Pasargadae was less a capital city and more a technological statement, proof that the Achaemenid Empire could reshape landscapes themselves. Satellite imaging and digital reconstruction have further deepened the mystery. Modern scans reveal symmetrical planning patterns difficult to fully recognize from ground level. Certain palace alignments appear intentionally positioned to create visual axes across the plain, guiding movement and attention with mathematical precision. What remains unclear is how Persian surveyors achieved these alignments with the technology available at the time. There is no evidence of advanced optical instruments, yet some measurements rival the accuracy of later classical civilizations. Even today, Pasargadae continues to confuse experts because it seems to appear suddenly in history already highly sophisticated. Unlike many ancient cities that evolve gradually over centuries, Pasargadae emerged within the reign of Cyrus as a remarkably organized and technically ambitious project. That sudden leap has led some historians to argue that the Achaemenids inherited forgotten engineering knowledge from earlier cultures of Mesopotamia and Elam. Others believe the empire's enormous scale allowed it to gather the greatest craftsmen of the ancient world into one place, accelerating technological development far beyond neighboring societies. Do you think the engineers of Pasargadae truly possessed knowledge far beyond their time, or are we still missing a crucial piece of history? Share your thoughts in the comments below. Beycesultan sits on a quiet mound in western Anatolia, near the Büyük-Menderes River basin in modern-day Turkey. In the 1950s, British archaeologists Seton Lloyd and James Mellart began excavating the site and uncovered something unexpected beneath layers of soil nearly 25 meters deep. The remains of a massive Bronze Age city occupied for thousands of years. What they found was not just another ruined settlement, but evidence of engineering techniques, architectural planning, and thermal management systems that appear strangely advanced for a civilization living nearly 4,000 years ago. The deeper archaeologists dug, the stranger Beycesultan became. Hidden beneath collapsed mud brick walls was a gigantic palace complex dating to roughly 1700–1500 BCE. The structure contained ceremonial halls, symmetrical corridors, elevated platforms, and thick foundation systems spread across a carefully organized layout. What shocked researchers most was the precision of the construction. The palace was built primarily from mud brick and timber, materials normally vulnerable to earthquakes, moisture, and erosion. Yet large sections of the structural base survived for millennia in one of the most seismically active regions of Anatolia. Modern engineers studying Bronze Age architecture have noted that Beycesultan's builders may have unintentionally, or intentionally, created an early form of seismic absorption. Beneath parts of the palace were multiple compressed soil layers mixed with clay and organic material. Similar principles appear in some earthquake-resistant Japanese foundations thousands of years later. The layered earth may have distributed seismic energy before it reached the upper walls. This is especially important because Western Anatolia sits near fault systems capable of generating destructive earthquakes even today. Compared to many Bronze Age settlements that completely collapsed under seismic stress, Beycesultan's lower structural platform remained unusually stable. One of the most mysterious discoveries inside the palace involved narrow channels and hollow spaces beneath the floors. Archaeologists originally assumed they were simple drainage systems, but later examinations suggested a more complex purpose. Some corridors appeared designed for controlled airflow rather than water movement. Several researchers proposed that the palace may have used passive ventilation to regulate temperature and humidity. If correct, Beycesultan possessed an architectural climate control system nearly 1,500 years before the famous Persian wind catchers and long before Roman hippocaust heating systems. The engineering logic behind this theory is surprisingly plausible. Warm air naturally rises while cooler air flows through lower channels. By directing airflow through shaded underground passages, ancient builders could reduce interior temperatures during Anatolia's hot summers. Modern passive cooling systems use similar principles. What makes Beycesultan extraordinary is the age of the structure. Most historians traditionally associate sophisticated environmental architecture with much later civilizations, yet Beycesultan may demonstrate that Bronze Age Anatolia already understood thermal regulation at a surprisingly advanced level. Another unexplained feature is the precision of the palace geometry. The spacing between wooden support columns appears remarkably consistent across large halls. Maintaining such symmetry without modern measuring instruments would have required standardized units and highly disciplined planning. Archaeologists have long debated whether Bronze Age Anatolia possessed formal systems of architectural measurement comparable to those later used in Egypt or Mesopotamia. At Beycesultan, some walls deviate by only a few centimeters across long sections, accuracy difficult to achieve even with simple rope-based measurement methods. This precision becomes even more mysterious when compared to other Bronze Age sites. At many settlements from the same period, buildings were expanded irregularly over generations, creating chaotic urban layouts. Beycesultan's palace, however, appears intentionally planned from the beginning. Some researchers believe the builders may have used geometric templates or proportional construction systems similar to those later seen in Minoan Crete. The comparison is important because artifacts discovered at Beycesultan suggest trade connections with the Aegean world. Pottery styles found at the site resemble ceramics from Crete and western coastal Anatolia, implying long-distance cultural exchange networks were already active. Trade may explain another of Beycesultan's greatest mysteries, its apparent wealth and influence despite its inland location. Excavations revealed imported materials, finely crafted ceramics, and evidence of large-scale storage facilities. Bronze production during this era depended heavily on tin, a rare material difficult to obtain in Anatolia itself. Since bronze requires roughly 90% copper and 10% tin, any civilization controlling tin routes possessed enormous economic power. Some historians suspect Beycesultan may have operated along one of the hidden trade corridors connecting Mesopotamia, central Anatolia, and the Aegean Sea. If that theory is correct, the city may have been part of an international Bronze Age economy far more interconnected than previously imagined. In fact, isotope studies of ancient metals across the Mediterranean have shown that Bronze Age trade networks stretched thousands of kilometers. Tin from Central Asia may have reached regions as distant as Greece and Egypt. Beycesultan's strategic location near river valleys would have allowed caravans and merchants to move materials efficiently across western Anatolia. Yet the most dramatic evidence at the site came from a catastrophic destruction layer. Archaeologists discovered thick bands of ash, charred beams, and intensely burned mud brick across major sections of the palace. The fire that destroyed Beycesultan around the 17th century BCE appears to have reached extremely high temperatures. In some areas, the mud brick became partially vitrified, meaning the clay hardened almost like ceramic after exposure to intense heat. Ordinary domestic fires rarely produce temperatures high enough for such transformations. This led to theories that the palace stored large quantities of oil, grain, timber resin, or other combustible materials. Some researchers even suggested that the city maintained centralized industrial storage facilities. Similar high-temperature destruction layers have been found at major Bronze Age sites such as Knossos and Hattusa, where palace economies controlled massive redistribution systems. In those societies, rulers collected agricultural goods, metals, oils, and textiles into centralized compounds. Beycesultan may have functioned in a similar way. The scale of the destruction raises another question. Was the fire accidental or the result of warfare? Evidence remains inconclusive. Unlike cities clearly destroyed by invasion, Beycesultan lacks overwhelming signs of mass slaughter or widespread weapon deposits. Some archaeologists believe the palace may have burned during political collapse or internal unrest rather than external conquest. Others argue the destruction could be linked to the broader instability that affected Bronze Age civilizations across Anatolia and the Eastern Mediterranean. Equally mysterious is the apparent decline of the settlement after its peak. Beycesultan was not suddenly abandoned overnight. Instead, the city gradually lost complexity over time. Monumental architecture disappeared, trade weakened, and later occupation layers became simpler. This pattern resembles the slow decline seen at sites like Mohenjo-Daro, where advanced urban systems faded without a single clear catastrophic event. Some scholars believe climate fluctuations may have reduced agricultural productivity across Anatolia during the Late Bronze Age. Others suspect economic fragmentation disrupted long-distance trade routes essential for sustaining elite palace centers. Even today, Beycesultan continues to produce unanswered questions. Ground-penetrating radar surveys suggest that large sections of the settlement remain buried beneath the mound. Some anomalies indicate the presence of additional underground chambers or unexplored architectural complexes. Archaeologists suspect that only a fraction of the city has actually been excavated. The most important structures, possibly archives, ritual chambers, or hydraulic systems, may still lie hidden underground. Do you think Beycesultan was simply ahead of its time? Or could ancient civilizations have possessed knowledge that modern history still does not fully understand? Share your thoughts in the comments below. Far across the Nazca Desert of southern Peru, a massive ceremonial city of mud pyramids rose in one of the driest places on Earth. Known as Cahuachi, the site was abandoned nearly 1,500 years ago, yet many of its fragile adobe structures still stand today despite earthquakes, floods, and centuries of erosion. Even more mysterious, the people who built it left behind advanced underground water systems, mathematically precise ceremonial alignments, and textiles whose colors remain visible after almost 2 millennia under brutal desert radiation. Although local people knew about the ruins for centuries, Cahuachi remained largely ignored until major archaeological investigations began during the 20th century. Extensive excavations led by Italian archaeologist Giuseppe Orefici revealed that the site was far larger than anyone expected. What initially appeared to be scattered hills turned out to be an enormous ceremonial complex covering nearly 24 square kilometers, containing pyramids, plazas, corridors, temples, burial areas, and elevated ceremonial platforms. Unlike cities such as Machu Picchu, Cahuachi was not designed as a permanent urban settlement. Archaeologists found surprisingly little evidence of large-scale daily domestic life. Instead, the site appears to have functioned as a gigantic pilgrimage and ritual center connected to the Nazca civilization between roughly 200 BC and 500 AD. That discovery immediately created a mystery. Why would a civilization build one of the largest ceremonial centers in ancient South America in the middle of an almost lifeless desert? The first major puzzle of Cahuachi is the survival of its architecture itself. Most of the structures were built from adobe bricks, sun-dried mud mixed with organic material. In many climates, adobe deteriorates rapidly through rain and seismic activity. Yet parts of Cahuachi have endured for nearly 2,000 years. The Great Pyramid alone rises roughly 28 meters high and required millions of adobe bricks. Researchers estimate that constructing the complex would have demanded enormous coordinated labor over generations. However, the Nazca civilization had no wheeled transport system in practical use, no large draft animals comparable to oxen or horses, and limited access to major timber resources. Even more unusual is the engineering beneath the structures. Excavations revealed that many foundations were not rigid. Instead, builders placed alternating layers of gravel, sand, and organic material beneath walls and ceremonial platforms. Some archaeologists believe this acted as a primitive seismic shock absorber. Modern earthquake-resistant buildings sometimes use flexible base isolation systems to absorb ground motion. While Cahuachi obviously did not possess modern engineering mathematics, the structural principle appears surprisingly similar. This is especially important because Peru lies along the Pacific Ring of Fire, one of the most seismically active regions on Earth. Many ancient mud brick cities across the Middle East collapsed after repeated earthquakes and rain exposure. Yet portions of Cahuachi survived both earthquakes and El Niño climate events that periodically brought destructive flooding into the Nazca region. Perhaps the most astonishing technological mystery surrounding Cahuachi involves water. The Nazca civilization constructed underground hydraulic systems known as pucuyos, spiral-shaped wells connected to subterranean aqueduct tunnels stretching across the desert. Some of these systems still function today after nearly 1,500 years. The Nazca Desert receives less than 25 millimeters of rainfall annually in some regions. In many areas, rainfall may not occur for years. Yet the Nazca managed to sustain ceremonial centers, agriculture, and population networks through underground water extraction systems engineered with remarkable precision. One of the greatest unanswered questions is how they identified underground aquifers without modern geological tools. Some tunnels maintain extremely accurate gradients over long distances, allowing water to flow naturally without collapsing the surrounding earth. Engineers studying the pucuyos discovered that many tunnels distribute pressure through carefully arranged stone placement, resembling primitive arch mechanics. Similar concepts later became essential in Roman aqueducts and medieval tunnel engineering. Yet the Nazca civilization left behind no written technical manuals explaining how this knowledge developed. Cahuachi may hold the key to understanding the famous Nazca lines. The ceremonial city sits near hundreds of giant geoglyphs carved into the desert, including animals, geometric shapes, and perfectly straight lines stretching for kilometers. Many researchers believe Cahuachi functioned as the religious center connected to these lines, with pilgrims traveling through ritual pathways across the desert. The real mystery is the precision of the geoglyphs. Some lines remain remarkably straight over vast distances despite uneven terrain, even though the Nazca had no aerial view or modern surveying technology. Several alignments also appear linked to solstices, sunrise positions, and seasonal cycles, suggesting the Nazca may have combined ritual activity, geometry, and astronomy into one massive ceremonial system. Excavations at Cahuachi uncovered evidence suggesting ritual violence once played an important role in Nazca religious life. Archaeologists discovered severed trophy heads with holes drilled through the forehead for ropes, and some even contained cactus spines placed inside the mouth. Researchers still debate whether these were war trophies or ceremonial offerings connected to rain and fertility rituals. Sediment analysis shows the Nazca region experienced powerful El Niño events that caused severe floods followed by long droughts. possibly leading to agricultural collapse. Some archaeologists believe the increase in sacrificial rituals reflected growing desperation as environmental conditions worsened. By the 5th or 6th century AD, Cahuachi appears to have been intentionally buried and abandoned. Several ceremonial areas were sealed beneath layers of earth, almost as if the Nazca were deliberately closing their sacred city. The most technologically mysterious aspect of Cahuachi may not be its pyramids or aqueducts, but its textiles. Archaeologists uncovered Nazca fabrics whose colours remain astonishingly vivid, despite nearly 2,000 years of exposure to one of the harshest UV environments on Earth. The Nazca civilization produced some of the most complex textiles in the ancient Americas. Certain fabrics contained up to 150 threads per inch, rivaling weaving precision achieved in far later civilizations. Some garments incorporated intricate embroidery, using dozens of color variations created from mineral, plant, and insect-based dyes. Scientists studying the pigments found remarkable chemical stability in several dyes. Red pigments often came from cochineal insects containing carminic acid, while blues, yellows, and blacks relied on complex mineral and botanical combinations. Under normal environmental conditions, many organic dyes should have faded centuries ago. Yet some Nazca textiles retained strong coloration after nearly 2 millennia, buried beneath desert sands exposed to intense solar radiation and dramatic temperature fluctuations. One explanation involves the extreme dryness of the Nazca Desert, which slowed biological decay. However, preservation alone does not fully explain the chemical durability of the pigments themselves. Researchers discovered that certain fibers may have undergone treatment processes involving mineral salts that stabilize color molecules at microscopic levels. Others suggest repeated dye layering techniques created deeper pigment penetration within the fibers. What makes this more mysterious is that the Nazca achieved this without iron vats, industrial fixatives, or synthetic chemistry. Even modern textile conservation experts remain impressed by the stability of some Nazca dyes. Comparisons have been made to Egyptian funerary textiles and ancient Andean Paracas fabrics, but Nazca textiles often display unusually intense chromatic preservation considering the environmental extremes. Some embroidered mantles also reveal astonishing symbolic complexity. Birds, mythical beings, decapitated heads, plants, and hybrid creatures appear woven into ceremonial garments with mathematical symmetry. Producing a single elite textile may have required months or even years of labor. To the Nazca, textiles were not simple clothing. They were technological objects, ceremonial symbols, status markers, and possibly even sacred offerings connected to cosmology and survival in the desert. What do you think the Nazca truly understood about engineering and science thousands of years ago? Let us know your theory in the comments below. Few kilometers from Persepolis, hidden beneath the cliffs of southern Iran, Naqsh-e Rajab preserves giant stone carvings so precise that even modern archaeologists struggle to explain how they were created nearly 1,800 years ago. The reliefs became known to Western archaeologists during 19th century explorations of ancient Persia, but detailed scientific studies only accelerated in the 20th century after high-resolution geological surveys revealed unusual carving precision, symmetry, and weather resistance across the monument. Naqsh-e Rajab was carved during the early Sasanian Empire, around the 3rd century AD, under rulers such as Ardashir I and Shapur I. The site contains massive royal reliefs cut directly into limestone cliffs, depicting coronations, noble ceremonies, and Zoroastrian symbolism. Compared to the towering ruins of Persepolis or the colossal Roman monuments of the same era, Naqsh-e Rajab appears modest at first glance. Yet archaeologists increasingly believe its technical sophistication may actually rival some of the greatest stoneworks of the ancient world. What makes the site unusual is that the reliefs were not assembled block by block like Roman architecture. Every figure, inscription, and geometric contour was carved directly into vertical mountain rock. Any major mistake would have permanently ruined the composition. Despite this, the symmetry across several relief panels remains astonishingly accurate. Some carved sections stretch several meters while maintaining nearly identical depth variations across entire surfaces. Researchers using laser surface analysis found deviations in certain decorative grooves, measuring only a few millimeters despite centuries of erosion. For comparison, many medieval stone carvings from Europe show far larger inconsistencies, even when produced with more advanced metal tools. This has raised a controversial question among historians. Did the Sasanians possess a level of stone planning technology far beyond what survives in written records? One of the greatest mysteries surrounding Naqsh-e Rajab is the precision of its carving technique. The folds of royal robes, curls of hair, horse anatomy, and crown decorations were cut into hard limestone with extraordinary consistency. Modern experiments conducted by experimental archaeologists have shown how difficult this should have been. Reproducing similar cuts using reconstructed Sasanian-era iron chisels often results in uneven surfaces, fractured edges, and tool slippage. Yet at Naqsh-e Rajab, many incision lines remain clean and controlled even under magnification. The cliff surface itself also presents a problem. Limestone in the region contains natural fracture zones that normally create unpredictable cracking during carving. However, the artisans somehow avoided catastrophic splits across enormous relief surfaces. Some geologists believe the craftsmen may have partially polished the stone using abrasive minerals like quartz sand before final detailing. Microscopic surface studies identified smoother finishing patterns in certain sections than would normally be expected from direct hammer and chisel work alone. This level of refinement is often compared to the precision seen in Achaemenid Persian carvings at Persepolis, or even certain Egyptian temple reliefs. But unlike Egyptian monuments, which were frequently carved on prepared blocks under controlled construction environments, Naqsh-e Rajab was sculpted directly into unstable cliff walls exposed to natural weathering. That makes the achievement even harder to explain. Another strange feature is how the reliefs interact with sunlight. The carvings were positioned on cliff angles that amplify shadows during sunrise and sunset. At certain times of year, sunlight strikes the royal crowns and facial structures first, creating dramatic illumination while the surrounding stone remains dark. Researchers studying solar orientation at the site discovered that several major figures face directions capable of maximizing visual contrast during specific daylight periods. The effect is subtle but deliberate. The kings appear almost animated as shifting shadows sharpen facial features throughout the day. This has led some scholars to compare Naqsh-e Rajab with solar-aligned architecture from ancient Egypt, Petra, and even certain Nabatean tombs. In Abu Simbel, for example, sunlight famously illuminates interior statues during particular seasonal alignments. Naqsh-e Rajab achieves a similar theatrical effect, but entirely through open-air cliff geometry rather than enclosed temple corridors. The mystery is whether the Sasanians intentionally engineered these lighting effects using astronomical observation, or whether the alignment was simply artistic intuition refined over generations. No surviving texts explain the process. The physical logistics behind Naqsh-e Rajab remain deeply puzzling. Several reliefs were carved high above ground level on steep cliff faces, yet archaeologists have found almost no permanent evidence of scaffolding systems, anchor holes, or construction platforms commonly associated with large-scale stone projects. Ancient Roman builders often left visible scaffold sockets in masonry structures. Even medieval cathedrals preserved traces of construction support systems. At Naqsh-e Rajab, these indicators are surprisingly scarce. Historians assume wooden scaffolds were temporarily inserted into natural rock fractures and later removed. But this explanation does not fully account for how teams maintained accurate proportions and carving consistency while working at dangerous heights on uneven surfaces. The larger royal figures measure several meters tall. Achieving proportional symmetry at that scale would normally require carefully measured guidelines visible from a distance. Yet almost none survive today. Some researchers suspect temporary pigment grids or charcoal planning systems may once have existed on the cliff surface before erosion erased them entirely. The most mysterious aspect of Naqsh-e Rajab may be its geometry. The proportions of the royal figures appear remarkably standardized. Head dimensions, shoulder width, arm positioning, horse anatomy, and ceremonial spacing repeatedly follow nearly identical ratios across separate reliefs. Modern image analysis comparisons suggest some body ratios differ by less than 3–5% between carvings created years apart. That level of consistency is extremely difficult to maintain in large-scale cliff sculpture without some form of underlying measurement system. This has led historians to propose that Sasanian artists may have used geometric planning grids similar to those employed in ancient Egypt. Egyptian tomb painters often divided human figures into proportional squares before carving. Greek sculptors later used mathematical ideals based on symmetry and anatomical balance. At Naqsh-e Rajab, however, almost no visible construction lines survive. The mystery becomes even stranger when examining perspective. Although the reliefs are relatively shallow, the artists manipulated depth carefully enough to create layered visual hierarchy. Royal figures appear dominant even when standing beside similarly sized attendants because of strategic positioning, carving depth, and spacing geometry. Some digital archaeologists have argued that the site demonstrates an advanced understanding of optical composition centuries before Renaissance perspective theory emerged in Europe. Even the placement of inscriptions seems mathematically organized. Pahlavi texts avoid interrupting visual balance while still remaining readable from below. This suggests that writing itself was integrated into the geometric design process rather than added afterward. If the Sasanians truly used hidden geometric frameworks, then much of their planning system has disappeared completely from the archaeological record. And that absence may be the greatest mystery of all. The inscriptions at Naqsh-e Rajab are carved with unusual depth and consistency. Some characters maintain nearly identical cutting angles despite being engraved across uneven cliff surfaces. Epigraphers studying the site noted that the inscriptions show strong line control rarely seen in exposed outdoor carvings from the same period. The precision becomes even more impressive considering the difficulty of carving flowing scripts into brittle limestone. In some areas, the cuts remain deep enough to cast sharp shadows after nearly 2 millennia of erosion. Researchers estimate portions of the reliefs have survived temperature fluctuations, ranging from near freezing winter nights to summer surface temperatures exceeding 50 degrees Celsius. Yet the inscriptions remain legible. This durability has fueled theories that the stone surface may have undergone additional finishing or treatment processes still poorly understood today. Tulum Archaeological Zone stood on the edge of the Caribbean Sea like a fortress designed to survive the impossible. Built atop 12-meter limestone cliffs in the middle of hurricane territory, the city should have collapsed centuries ago. Instead, its walls still face salt winds, tropical storms, and relentless erosion. Even stranger, one temple inside Tulum appears to use aerodynamic principles that modern engineers would not formally understand until hundreds of years later. Archaeologists first documented Tulum extensively during the mid-19th century after explorers John Lloyd Stephens and Frederick Catherwood travelled through the Yucatan Peninsula and reported a walled Maya city overlooking the sea. Later excavations revealed that Tulum was not simply ceremonial. It functioned as a fortified maritime trading port, connected to routes stretching across Central America and the Caribbean. Most ancient coastal settlements gradually disappear under erosion, salt corrosion, or hurricanes. Tulum somehow resisted all three. The city was constructed directly on porous limestone cliffs facing the Caribbean, an environment modern engineers consider extremely hostile for long-term structural survival. Salt water is one of the most destructive natural forces for stone architecture. Sodium chloride penetrates microscopic cracks, expands during moisture cycles, and slowly fractures masonry from within. Modern reinforced concrete near coastlines often deteriorates within decades without protection. Yet parts of Tulum's walls have survived for over 700 years. The mystery becomes more serious when examining the foundation system. Unlike Roman structures that relied on massive deep foundations, the Maya distributed weight across broad limestone platforms using tightly fitted stone blocks. Many walls contain tiny expansion gaps that may have allowed slight movement during storms, preventing catastrophic cracking. Some structural engineers compare this concept to primitive seismic flexibility seen in certain Japanese wooden temples. Tulum also sits in one of the most hurricane-prone regions in the Americas. Modern hurricanes in the Yucatan have produced winds exceeding 250 kilometers per hour. Despite this, many core structures remain partially intact. The low and thick geometry of Maya construction appears deliberately optimized against overturning forces caused by extreme winds. Even more puzzling is site placement. Much of the Yucatan Peninsula contains unstable underground voids and sinkholes formed by dissolved limestone. Yet the primary temples were built on some of the most geologically stable portions of the cliff edge. Without radar or subsurface imaging, the Maya somehow avoided the most dangerous collapse zones. Temple of the Wind. God may be the most technologically mysterious structure in the entire city. Unlike the rigid rectangular geometry common in Maya architecture, this temple contains rounded edges and curved surfaces that appear intentionally designed to interact with airflow. At first glance, the shape seems decorative, but aerodynamic simulations conducted by modern researchers suggest otherwise. When exposed to strong coastal winds, sharp rectangular buildings create turbulent vortices that increase pressure stress on corners and walls. Curved surfaces reduce these pressure concentrations by redirecting airflow around the structure. This principle is now fundamental in modern aerodynamic engineering. It is used in skyscrapers, aircraft fuselages, and even Formula One design. Yet the Maya built this structure between the 13th and 15th centuries without mathematical, fluid dynamics, wind tunnels, or modern physics. Computer simulations comparing the Wind Temple to standard rectangular Maya buildings indicate the curved profile significantly lowers wind resistance during storm conditions. Some researchers believe the rounded geometry helped prevent vortex shedding, a dangerous oscillation effect capable of destroying bridges and towers. The collapse of the Tacoma Narrows Bridge in 1940 demonstrated how devastating uncontrolled aerodynamic resonance can become. Tulum's builders may have discovered primitive methods of reducing similar forces centuries earlier. Several walls also lean at subtle angles rather than remaining perfectly vertical. This could have helped redirect wind loads downward into the structure rather than allowing direct lateral impact. Similar concepts appear in some cyclone-resistant modern buildings. The mystery is not simply that the temple survived. The mystery is how the Maya recognized these principles at all. There is no evidence they possessed theoretical physics in the modern sense. One possibility is that centuries of observing hurricanes forced builders into an advanced empirical engineering tradition, where structures were refined generation after generation through real environmental testing. Another theory suggests the temple's position also served navigational purposes. Fires lit inside the upper openings may have acted as visual markers for canoes approaching the reef passages offshore. The structure therefore may have functioned simultaneously as a wind-optimized building, storm-resistant lookout tower, and maritime beacon. If true, the wind temple would represent one of the earliest known examples of environmental aerodynamic architecture in human history. Tulum challenges the common image of the Maya as an isolated jungle civilization. Archaeological evidence increasingly suggests they operated a highly sophisticated maritime trade network along the Caribbean coast. The waters near Tulum are extremely dangerous because of coral reefs located just offshore. Even modern boats without accurate navigation charts risk collision. Yet ancient Maya traders routinely navigated these waters using large dugout canoes capable of carrying dozens of people and heavy cargo. Researchers discovered that certain temple windows and sightlines align with narrow openings in the reef system. At night, fires or reflected moonlight from these structures may have guided vessels towards safe passages. The navigational margin for error would have been extremely small, possibly only a few degrees. This raises deeper questions about Maya astronomy and coastal mapping. The civilization already possessed highly accurate solar and Venus calendars. Some historians now suspect these astronomical systems were also connected to maritime orientation and seasonal ocean travel. Compared to many inland civilizations of the same period, the Maya may have possessed a far more advanced understanding of coastal environmental systems than previously believed. One of Tulum's least understood technologies is its construction material. Coastal humidity and salt normally destroy lime mortar over time, yet many sections of Maya masonry remain remarkably durable. Chemical analysis shows the Maya used burned limestone mixed with local mineral aggregates and organic additives. Some samples exhibit weak pozzolanic reactions, similar to ancient Roman marine concrete. Roman engineers used volcanic ash to create water-resistant cement capable of surviving seawater for thousands of years. But the Yucatan Peninsula lacks the massive volcanic ash sources found in Italy. This has led researchers to suspect the Maya developed alternative formulas using crushed shells, coral particles, plant resins, or even organic compounds from coastal vegetation. Some scientists believe these materials may have created primitive biocomposite binders capable of resisting moisture penetration. Modern sustainable engineering increasingly experiments with bio-based construction materials remarkably similar in concept to these ancient mixtures. Yet the exact Maya formula remains unknown. Underneath Tulum lies another hidden world, an immense network of cenotes and flooded cave systems stretching for hundreds of kilometers beneath the Yucatan Peninsula. These underground systems are among the largest submerged cave networks on Earth. The danger is that limestone ceilings can collapse unpredictably, creating massive sinkholes. Building a city above such terrain without geological knowledge would have been extremely risky. Yet major structures at Tulum appear positioned away from the most unstable underground chambers. Some researchers speculate that the Maya identified safe zones through subtle environmental clues such as ground vibration, water sounds, airflow changes, or soil behavior. Others believe generations of accumulated local knowledge allowed them to map underground conditions with surprising accuracy. Even today, modern explorers continue discovering new tunnels and submerged chambers beneath the region, using advanced diving technology and LiDAR scanning. Do you think Tulum disappeared because of disease and climate collapse? Or was an advanced knowledge system lost with the civilization itself? Share your theory in the comments below.